The universe is a gallery of unsolved mysteries. In its vast expanse, one celestial giant holds more secrets than almost any other, the supergiant elliptical galaxy Messier 87. This is the home of the first black hole humanity ever photographed, a place of immense gravity and brilliant, violent light. But that iconic image is just the beginning. We are embarking on a cosmic safari to uncover 50 of the strangest objects hidden within this galactic giant. You will discover bizarre stars, ghostly structures, and cosmic anomalies that defy simple explanation. What force creates a beam of plasma stretching for thousands of light years? How can a galaxy be both ancient and seemingly young? By the end, you will have a front row seat to the most extreme physics and puzzling phenomena in the modern cosmos. This is a journey to the very edges of our understanding. What do you think is the universe's strangest hidden rule? At the heart of this galactic giant lies a cosmic monster of almost unimaginable scale. This is the supermassive black hole known as M87 star, the first black hole humanity ever directly saw. That iconic image, a fiery ring of light surrounding a dark central void, was not a photograph in the traditional sense. It was a monumental achievement of global cooperation, stitching together data from radio telescopes across the planet to form a virtual telescope the size of Earth itself. This was the work of the Event Horizon Telescope, and what it revealed was both beautiful and terrifying. The dark center is not the black hole itself, for a black hole, by definition, emits no light. What we see is its shadow, a silhouette cast against the glowing, superheated gas swirling around it at nearly the speed of light. This shadow is the point of no return, the event horizon, where the pull of gravity becomes so intense that not even light can escape. The size of that shadow allowed scientists to calculate the black hole's mass, a number that is genuinely difficult to comprehend. M87 star weighs in at 6.5 billion times the mass of our Sun. To put that in perspective, you could fit every single star in our entire Milky Way galaxy inside it several times over. But the strangeness does not stop at its immense gravity. Emanating from its poles is one of the most spectacular and violent features in the universe, a relativistic jet. This is a concentrated beam of matter and energy, plasma heated to billions of degrees and accelerated to over 99% the speed of light. It stretches out from the galaxy's core for an astonishing 5,000 light-years, a searing, straight line that pierces the cosmic dark. Studying this jet and the shadow of M87 star is like conducting the ultimate laboratory experiment. It allows physicists to test Einstein's theory of general relativity under the most extreme conditions possible, in places where space and time are warped beyond recognition. Every observation is a question, probing whether our understanding of gravity holds true at the very edge of a bottomless pit. That colossal jet of energy is not a smooth, uniform river of light. Peer closely into its brilliant stream, and you will find turbulent knots and violent hotspots like whirlpools in a raging cosmic current. The strangest of all is a feature known as HST1. Discovered by the Hubble Space Telescope, this is a distinct, intensely bright knot embedded within the jet itself, located surprisingly close to the galactic core. For years, astronomers considered it a stable part of the jet's structure, a mere bump in the road. Then, without warning, it began to misbehave. Starting around the year 2000, HST1 erupted. It did not just brighten a little, it underwent a series of dramatic, violent flares. In X-ray light, its brightness increased by a staggering factor of 100, outshining even the supermassive black hole at the galaxy's heart for a period of time. This was not a slow change, it was a sudden, explosive event happening within a structure we thought we understood. What could cause such a localized cataclysm? The leading theories sound like chapters from a book on extreme astrophysics. One idea involves powerful shock waves. Imagine material flowing down the jet at different speeds colliding, creating a cosmic traffic jam that releases an enormous burst of energy, like a sonic boom in plasma. Another compelling possibility is magnetic reconnection, a process where the powerful magnetic fields threading the jet suddenly snap and reconfigure, converting magnetic energy directly into radiation and heat in an instant. But there is a more exotic and tantalizing explanation. Some scientists speculate that HST-1 could be the signature of a second, smaller black hole orbiting the primary monster. As this smaller black hole feeds, it could inject extra energy into the jet at that specific point, creating a persistent, flaring hotspot. This would mean the heart of Messier 87 is not a solitary titan, but a dancing pair of gravitational demons, one feeding the other and lighting a fire along their shared jet. The flares have since subsided, but HST-1 remains a stark reminder. Even the most well-studied cosmic structures can harbor profound, explosive secrets, challenging our models and forcing us to look deeper. This brilliant asymmetry is one of the most visually striking puzzles in all of astronomy. We see one jet, a blazing searchlight stretching across the cosmos. But look in the exact opposite direction from the black hole, and you find its twin, the counter-jet. It is there, but it is ghostly, faint, and appears startlingly short. This is not an illusion, it is a profound clue written in light and shadow. A simple, symmetrical engine should shoot two identical beams in opposite directions. So why does reality look so lopsided? The answer lies in one of the most mind-bending consequences of Einstein's relativity, a phenomenon called relativistic beaming. Picture the material in that jet not as a serene flow, but as a fire hose of plasma blasted outward at over 99% the speed of light. At such incredible velocities, the very nature of light itself changes from our perspective. The radiation emitted by the jet is not just streaming away, it is being focused or beamed intensely forward in the direction of motion. It is like the sonic boom of a jet fighter, but made of light. If you are standing directly in front of that onrushing wall of energy, it appears dazzlingly bright. But if you are off to the side, or worse, looking at it from behind, it seems dim. In the case of Messier 87, astronomers believe the main, brilliant jet is pointed very nearly toward our line of sight. We are getting a nearly head-on view of its concentrated beam, amplifying its brilliance. The counter-jet, by necessity, is pointing almost directly away from us. We are seeing it from behind, catching only the faint, scattered glow that manages to escape backward. This effect alone can explain much of the dramatic difference in brightness, but the story may have even more layers. Could something be physically blocking the counter-jet? Many active galaxies possess a thick, donut-shaped structure of gas and dust called a torus, swirling around the central black hole. If such a torus exists in Messier 87 and is slightly misaligned, it could be obscuring our view of the counter-jet's base, making it appear truncated and faint. Or perhaps the engine itself is not perfectly symmetrical. The chaotic magnetic fields or the flow of accreting matter onto the black hole could be intrinsically lopsided, feeding one jet more powerfully than the other. The faint counterjet forces us to abandon simple, pretty models of the cosmos. It reminds us that our viewpoint in the universe is not a neutral one, and that the extreme physics near a black hole can twist reality into shapes we are only beginning to decode. Amidst that brilliant maelstrom of light and energy, there are also shadows. High-resolution images from the Hubble Space Telescope reveal a haunting detail silhouetted against the galaxy's glowing core, delicate, thread-like tendrils of darkness. Astronomers call them the dark lane filaments. They look like ghostly cobwebs or the delicate veins in a marble, but these are not peaceful structures. They are colossal ropes of cold molecular gas and dust, some stretching for hundreds of light years, drifting perilously close to the galactic inferno. Their very existence here is a paradox. How can such fragile, cold material survive so near to a region that blasts everything with intense radiation and gravitational fury? The answer is as violent as it is fascinating. These filaments are not simply floating, they are being actively shredded. The immense tidal forces from the supermassive black hole, combined with the blistering pressure of radiation from the hot gas around it, are stretching and tearing these clouds apart. They are cosmic taffy, pulled into long, thin strands before they are ultimately vaporized or drawn into the accretion disk. This raises a profound question: where did this cold gas come from in the first place? One compelling theory is one of galactic cannibalism. Messier 87 is a supergiant elliptical galaxy, and such behemoths grow by consuming their smaller neighbors. The dark lane filaments could be the last visible remnants of a dwarf galaxy that ventured too close. As it was torn apart by M87's gravity, its cold gas and stars were strewn out into these long, streaming filaments, a cosmic crime scene marked by these dark, dusty trails. Another possibility is that they formed in place, condensing directly out of the hot intergalactic medium that suffuses the galaxy, like mist forming on a cold windowpane. This process, called thermal instability, would see pockets of the superheated gas suddenly cool and collapse into these dense, dark threads, only to be immediately assaulted by the very environment that created them. These dark lanes are more than just pretty shadows, they are forensic evidence. By studying their motion and composition, astronomers can trace the history of violence in the galaxy's core, measure the powerful forces at work, and perhaps even clock the last meal of a hungry galactic giant. They are a silent testament to the fact that even in the brightest places, the universe writes its history in strands of darkness. The delicate filaments are not the only ghosts haunting this galaxy's vast halo. Messier 87 is encircled by a staggering swarm of stellar cities, ancient globular clusters that number over 12,000. To grasp that scale, our own Milky Way galaxy, no small cosmic structure itself, holds only about 150. This is a difference not of degree but of kind. Within that immense population, astronomers have identified a strange and elusive class, the ultra-faint globular clusters. These objects are so dim, so diffuse, they exist in a shadowy borderland. They blur the fundamental line astronomers draw between a star cluster and a dwarf galaxy. A typical globular cluster is a dense, spherical ball of hundreds of thousands of ancient stars, bound tightly together by gravity. These ultra-faint clusters, however, are far more tenuous. They contain far fewer stars, and those stars are spread out over a much larger volume, making them incredibly difficult to spot against the black velvet of space. Finding them is like trying to see a faint wisp of smoke from thousands of miles away. So what are they? Their strange nature points to two dramatic origin stories, each a chapter in the violent history of this galactic giant. The first theory is one of cosmic demolition. As Messier 87 cannibalized smaller satellite galaxies over billions of years, it did not always consume them whole. The immense tidal forces could strip away a dwarf galaxy's outer stars, leaving only its dense, star-packed core behind. This surviving core, now adrift and orphaned in M87's halo, would look exactly like an ultra-faint globular cluster, a ghostly remnant of a galaxy that once was. The second possibility is even more intriguing. Perhaps these clusters represent a unique, primordial mode of star formation that occurred only in the extreme conditions of the early universe, within the vast halos of the first supergiant galaxies. In this scenario, they were never part of a larger galaxy. They formed as these faint, extended clusters from the very beginning, fossils from an era when the rules of star birth were fundamentally different. Each ultra-faint cluster we find is therefore a cosmic archaeological artifact. Is it the stripped nucleus of a devoured neighbor, a trophy from a past conquest? Or is it a pristine relic from the dawn of galactic time, a whisper from the universe's first chapters. Their dim light holds the answer to how the largest structures in the cosmos built themselves piece by ancient piece. Even the most tightly bound stars can be thrown into a desperate galactic escape. Among the ancient stellar populations of Messier 87, astronomers hunt for rare and elusive exiles, hypervelocity star candidates. These are stars moving so fast they approach or even exceed the galaxy's own escape velocity, the speed needed to break free from its immense gravitational grip forever. Picture a star not as a fixed point of light, but as a cosmic projectile, flung out from the galactic core with such force that it is destined for the lonely void of intergalactic space. The energies required for such a feat are almost unimaginable, pointing to only a few possible origins, each a story of extreme gravitational violence. The prime suspect is the chaotic dance at the galaxy's very heart. If, as some evidence suggests, the supermassive black hole M87 star is not alone but has a smaller companion black hole, their orbital waltz creates a natural and devastating slingshot. A star that wanders too close to this binary pair can be caught in a complex gravitational tug-of-war. Instead of being consumed, it can be whipped around one of the black holes and catapulted outward at a significant fraction of the speed of light, like a stone from a giant sling. Another potential mechanism involves the brutal dissolution of a binary star system. Imagine two stars orbiting each other closely. If they drift perilously near the single or binary black hole, the gravitational forces can tear the pair apart. One star gets captured into a tight orbit around the black hole, while its former partner is ejected at tremendous speed, recoiling from the encounter like a bullet from a rifle. Identifying these stars within Messier 87, however, is a monumental challenge across 55 million light-years. Astronomers cannot track their motion in real time. Instead, they rely on precise measurements of a star's light. By analyzing the subtle shift in its spectral lines, a phenomenon called the Doppler effect, they can calculate its radial velocity, how fast it is moving directly toward or away from us. A star showing an exceptionally high radial velocity could be a candidate hypervelocity star, but confirming it requires ruling out other explanations and ideally detecting its proper motion, its actual movement across the sky, which is exceedingly difficult at such distances. Each confirmed candidate would be a direct tracer of the most powerful gravitational events in the universe. They are the smoking guns of black hole interactions, celestial evidence that records a cataclysmic encounter that happened millions of years ago. Finding them tells us not just about the stars themselves, but about the hidden dynamics of the monster that launched them, mapping the invisible forces at play in the galaxy's dark heart. The precise center of a galaxy should be its most stable, anchored point. Yet for Messier 87, the brightest beacon of light and the true gravitational heart may not be in the same place. This is the mystery of the offset active galactic nucleus, the photometric center, the brightest concentration of starlight that defines the galaxy's visual core, and the dynamical center, the point around which everything orbits, dictated by the supermassive black hole's gravity, appear subtly misaligned. It is as if the monstrous engine at the galaxy's core is not sitting perfectly still, but is instead slightly off balance, creating a barely perceptible wobble in the cosmic order. How could such a thing happen to an object with 6.5 billion times the mass of our Sun? The leading explanation is a story of recent violent change. Imagine a cosmic collision, a merger between Messier 87 and another sizable galaxy within the last few 100 million years. During such an event, the supermassive black holes at the center of each galaxy would begin a spiraling dance, eventually coalescing into one. But the aftermath is not instant calm. The newly formed, more massive black hole can be given a powerful kick from the gravitational waves emitted during the merger's final moments, like the recoil from a cannon. This kick could send it oscillating through the core, a process called dynamical friction, as it plows through the surrounding stars and gas, slowly sinking back toward the true center over eons. We could be witnessing it on its long, slow journey home, a titan finding its footing after a catastrophic union. There is another, even more profound possibility. The offset might not be a movement of the black hole itself, but a distortion of the very stage upon which it sits. The true gravitational center of the galaxy is not defined by starlight alone, but by the immense invisible halo of dark matter that envelops everything. If this dark matter halo is not perfectly smooth and symmetrical, if it is lumpy or elongated in a particular way, it can shift the location of the deepest part of the gravitational well. The black hole would simply reside at the bottom of this well, even if that bottom is not perfectly aligned with the glow of the stars. This would mean the offset is a direct map of the hidden dark matter skeleton of the entire galaxy, a ghostly hand subtly pulling the visible universe out of alignment. Determining which of these stories is true is a delicate task of cosmic measurement. It requires painstakingly mapping the motions of thousands of stars near the core to pinpoint the exact gravitational center, and then comparing it with the peak of the light distribution. A confirmed, significant offset would be a monumental clue. It would either be a timestamp of a recent dramatic merger, or it would provide a rare and precious window into the invisible architecture of dark matter that shapes all we see. The quiet misalignment of a single point of light could therefore tell one of two epic tales, a story of a past collision or a map of the universe's greatest unseen force. The brilliant violence of that jet might suggest a ravenous, endlessly feeding monster, but the light from the core itself tells a more nuanced and puzzling story. Messier 87's active nucleus belongs to a peculiar class known as a LINER, or low ionization nuclear emission region. This technical term reveals a crucial secret about the state of the galactic heart. Unlike the dazzling, high-energy furnaces of quasars that shred atoms completely, the gas swirling around M87's black hole is only lightly ionized. It is being gently stirred, not violently blasted. Think of it as the difference between a roaring bonfire and the soft, steady glow of embers. Both indicate heat, but one speaks of a raging inferno, the other of a more subdued, smoldering state. This spectral signature points directly to the black hole's feeding habits. The leading idea is that M87 star is currently in a low fuel or radio mode state. Instead of a continuous, dense feast of gas funneling into its maw, it may be nibbling on a more diffuse, tenuous diet. The accretion disk, the swirling platter of superheated material that powers the entire engine, could be inefficient and patchy. In this scenario, the black hole is not starving, but it is certainly not dining with the voracious appetite needed to power a brilliant quasar. There is, however, a compelling alternative that complicates this picture. What if the gas itself is in a different physical condition altogether? The models suggest that if the infalling material is especially dusty or in a unique, low-density state, it could naturally produce this lower ionization signature even if the central engine is quite powerful. It would be like trying to start a fire with damp wood. You get a lot of smoke and a low, smoky flame, not a clear, hot blaze. This means the LINER classification might not be a simple indicator of the black hole's appetite, but a clue about the specific menu it is being served. This ambiguity forces astronomers to reinterpret everything they see. That magnificent jet, stretching for thousands of light years, is clearly drawing immense power from somewhere. So how can the core appear so relatively quiet? The answer may lie in the efficiency of the engine itself. In this radio mode state, a greater fraction of the accreted energy might be channeled directly into launching and sustaining that colossal jet, rather than being radiated away as intense light from the disk. The black hole could be a master of conversion, taking a modest meal and using it with extreme precision to power a cosmic blowtorch, while keeping its own immediate surroundings deceptively dim. The LINER is therefore not a sign of weakness but a diagnostic tool. It tells us we are looking at a giant in a specific phase of its life, possibly between more violent feeding frenzies, or one that has perfected a different way of expressing its power. The soft glow at its center is a quiet puzzle, challenging us to understand how such a gentle light can be the birthplace of such an ungentle force. The galaxy's core is not the only place marked by the black hole's power. Far out in the vast ocean of hot gas that envelops Messier 87, astronomers have found enormous, ghostly imprints, the mysterious X-ray cavities. In visible light, this region appears as a smooth, diffuse haze, but switch to the piercing vision of an X-ray telescope like Chandra and the scene transforms. The hot gas, glowing at millions of degrees, reveals two vast, bubble-like voids, one on either side of the galactic center. They are not truly empty, but are instead colossal pockets of lower density, like bubbles rising in a pot of cosmic soup. Their scale is staggering, each one large enough to swallow thousands of solar systems. The origin of these cavities is a direct result of that incredible relativistic jet. For millions of years, the jet has not simply been a beam of light. It has been a physical piston, relentlessly pushing its way through the surrounding intergalactic gas. It excavates these immense volumes, clearing out the hot plasma and filling the space left behind with something else, a powerful mix of magnetic fields and ultra-high energy particles called cosmic rays. This makes each cavity a giant, invisible balloon of pure energy, buoyantly floating outward from the galaxy's heart. These structures are far more than just scars, they are a fossil record. The size and distance of the cavities from the core act as a cosmic clock. By measuring how far they have risen and calculating how quickly they would buoyantly rise through the hot gas, astronomers can estimate when the jet that created them was most active. It is like finding layers of ash in sediment, each layer corresponding to a past volcanic eruption. In Messier 87, the cavities reveal that the central black hole has experienced powerful outbursts every few tens of millions of years, episodic frenzies of activity punctuating its quieter periods. This cyclical behavior has a profound effect on the entire galaxy cluster. The cavities play a crucial role in a grand cosmic regulatory system, a feedback loop that prevents the universe from turning all its gas into stars. As these magnetic and cosmic ray-filled bubbles rise and eventually disrupt, they release their stored energy back into the surrounding gas, gently heating it. This added heat keeps the gas from cooling, collapsing, and forming vast numbers of new stars. Without this black hole-driven heating, the galaxy cluster would likely be a dazzling, star-forming factory, but one that would quickly burn through its fuel. The supermassive black hole, through its jet and these fossilized bubbles, acts as a cosmic thermostat, regulating the growth of its own galaxy and maintaining a delicate billion-year balance between creation and stillness. That colossal jet is just the brightest thread in a much larger tapestry of radio light. Surrounding Messier 87 and stretching far into the heart of the Virgo Cluster is a vast, diffuse sea of radio emission, a ghostly halo that dwarfs even the galaxy itself. This is not a smooth, uniform glow, but a complex structure of faint wisps and large-scale relics, a faint whisper of radio waves that tells a story of ancient violence on a truly epic scale. To see it, you need the collective ear of a radio telescope array, listening not to light, but to the synchrotron radiation emitted by electrons spiraling at nearly the speed of light through weak magnetic fields. These aren't the electrons from the current jet, they are the aging remnants of events that occurred hundreds of millions of years ago. The leading theory is one of immense turbulence. As Messier 87 plowed through the dense intergalactic gas of the Virgo Cluster, or as it merged with other galaxies, it would have generated colossal shock waves, rippling through the cluster medium like sonic booms from a cosmic explosion. These shocks act as natural particle accelerators, giving electrons a tremendous kick, boosting them to relativistic speeds. Once energized, these electrons become trapped in the cluster's magnetic fields, spiraling for eons and emitting the faint radio glow we detect today. The halo is therefore a fossil, a lingering afterglow of past cataclysms. Its very existence and detailed structure are a direct record of the galaxy's dynamic history, a history written not in stone or starlight, but in the slow dance of high-energy particles and magnetic fields. By mapping the subtle contours and brightness of this radio fog, astronomers can essentially perform cosmic archaeology, reconstructing the timing and ferocity of ancient mergers and collisions that shaped the galaxy we see today. It is a reminder that a galaxy's present form is only the latest frame in a long, violent film, and that the echoes of its past are still ringing faintly across the electromagnetic spectrum. The faint radio whispers of the past are punctuated by moments of sudden, brilliant violence. Among the most dramatic are the fleeting signatures of a star's final, catastrophic encounter, the tidal disruption event. In the vast stellar swarm of Messier 87, astronomers are hunting for the telltale flares of not one, but at least two potential candidates where a star ventured fatally close to the central monster. Imagine the journey of such a star, perhaps one from the crowded core, nudged by gravitational interactions onto a doomed orbit. As it spirals inward, the difference in the black hole's gravitational pull on the star's near side versus its far side becomes overwhelming. This tidal force stretches the star horizontally while compressing it vertically, a process called spaghettification, until it is torn apart into a long, thin stream of gas. This is not a quiet end. The stellar debris does not vanish instantly. About half of it is flung away into the darkness, while the other half swings back around to form a swirling, temporary accretion disk around the black hole. As this disk forms and the gas compresses and heats, it ignites a tremendous flare of light across the electromagnetic spectrum, from X-rays to visible light, that can briefly outshine the combined light of every star in the galaxy. This flare rises to a peak over weeks or months, and then slowly fades over years as the last of the stellar material is consumed. Spotting such a flare in a giant elliptical like Messier 87, however, is like trying to see a match struck in front of a floodlight. The galaxy's constant, low-level active galactic nucleus activity provides a steady background glow against which a transient flare must stand out. Astronomers must meticulously monitor the galaxy's brightness over years, looking for subtle, unexpected increases that have the specific color and timing signature of a tidal disruption event, while ruling out other causes like a supernova or a jet flare. Confirming even one of these candidates would be a scientific bonanza. It would offer a pristine, controlled experiment in black hole feeding. Unlike the messy, continuous accretion from interstellar gas, a tidal disruption event provides a known quantity of fuel, a single star of roughly known composition and mass. By watching how the black hole consumes this specific meal, how the light evolves and fades, physicists can test models of accretion physics with unprecedented precision. It would reveal the black hole's appetite in real time and give us a clean measurement of its properties, separate from the complex, ongoing activity of its core. Each suspected flare is therefore a potential treasure, a chance to witness a rare cosmic autopsy and understand the final moments when a star becomes a black hole's dinner. But the galaxy's appetite for destruction is not confined to its central monster. Scattered across its vast expanse are strange, brilliant beacons of pure X-ray light, points of intensity that defy simple classification. These are the ultra-luminous X-ray sources, or ULXS. Each one appears as a single, tiny point in our telescopes, yet it shines with the power of millions of suns, but only in the highest energy X-ray part of the spectrum. They are not the supermassive black hole, they are something else entirely, and their very presence in an ancient elliptical galaxy like Messier 87 is a profound puzzle. In a galaxy dominated by old, red stars, where should such luminous, energetic objects come from? The power they emit is so great that it pushes against a fundamental limit in astrophysics, the Eddington limit. This is the theoretical maximum brightness a celestial object can achieve from spherical accretion before the pressure of its own radiation blows the incoming fuel away, like a wind so strong it prevents more leaves from falling onto a fire. To shine as brightly as these ULXS, an object must either be more massive than a typical star, or it must be feeding in a way that breaks the usual rules. This leads to two thrilling possibilities, each representing a different kind of cosmic extreme. The first is that these are stellar mass black holes or neutron stars, the dense corpses of dead stars, but they are feeding at super Eddington rates. Imagine a black hole with the mass of 10 suns, but it is pulling in gas so rapidly, so greedily, that the infalling material forms a thick, puffy envelope. Radiation struggles to escape this shroud, and the accretion becomes funneled, not spherical. This allows the object to temporarily bypass the Eddington limit, shining with a stolen brilliance far beyond what its mass should allow. It is a cosmic glutton, overeating in a spectacular fashion. The second possibility is even more significant. These brilliant points could be the long-sought missing links, intermediate mass black holes. These would be objects with masses ranging from a few hundred to a few 100,000 times that of our Sun, filling the vast gulf between the stellar mass black holes born from dying stars and the supermassive giants that rule galactic centers. An intermediate mass black hole accreting normally could easily explain the tremendous X-ray output of a ULX. Finding one would be a cornerstone discovery, providing a crucial clue to how the supermassive black holes like M87 star grew to such immense sizes. Did they start as these intermediate seeds and merge repeatedly, or did they form through some other, more direct collapse? Each ultra-luminous X-ray source in Messier 87 is therefore a potential Rosetta Stone. Its light holds the key to understanding either the most violent feeding modes of small compact objects, or it reveals the existence of a whole new class of black hole, a middle child of the cosmos hiding in plain sight. Their brilliant, hard X-ray glow is a challenge, a direct question about the limits of physics and the hidden population of monsters lurking in the dark. That ancient sea of red stars holds a secret youth hidden within its depths. While the vast majority of Messier 87 stars are indeed old, red, and long past their star-forming prime, astronomers have discovered puzzling pockets that tell a different story. Scattered through the galaxy, particularly in its outer regions, are subtle signs of stellar populations that appear suspiciously young, perhaps only a few 100 million years old. This is the cosmic equivalent of finding a toddler in a retirement home, a profound contradiction in a galaxy famously labeled red and dead. The very phrase describes elliptical galaxies perfectly. They are dominated by ancient, cool, red stars with no ongoing star formation and no reservoirs of cold gas to fuel it. So how could a new generation of stars possibly ignite here? The mystery points directly to a hidden source of fuel, a sudden, recent injection of cold gas that should not exist. One compelling theory looks inward to the galaxy's own vast atmosphere. Enveloping Messier 87 is a massive halo of multimillion-degree gas detectable in X-rays. Could small pockets of this superheated plasma have somehow cooled, condensed, and collapsed into dense, cold clouds capable of forming stars? This process, called thermal instability, is like watching steam suddenly condense into droplets on a windowpane. While possible, it is a slow and delicate process in the face of the black hole's periodic outbursts, which constantly reheat the halo gas. For stars to form this way, a pocket of gas would have to cool in a quiet interval, untouched by any jet-driven heating for tens of millions of years. The other explanation is a story of galactic theft. Messier 87 is a cannibal, and its last meal may have been very recent. Imagine a small, gas-rich dwarf galaxy or a large gas cloud straying too close. As it was torn apart by tidal forces, its pristine, cold gas would have been stripped away and funneled into the giant. This fresh fuel, raining down into the outer regions of Messier 87, could have triggered a brief, localized burst of star formation before the intense environment of the giant galaxy shut it down. The young stars we see today would be the living evidence of that recent minor merger, a final flash of creation before the gas was heated, dispersed, or consumed. Finding these young populations is a forensic challenge. Astronomers must use the precise colors and spectral signatures of starlight to disentangle the faint blue glow of young, hot stars from the overwhelming red glare of the ancient majority. Each confirmed pocket is a timestamp, marking either a moment of unexpected internal cooling or the last gasp of a devoured neighbor, proving that even in a galaxy of ancient giants, the story of birth is not entirely over. The young stars are a fleeting signature, but the true, unseen ruler of Messier 87 is far more permanent and profoundly strange. To understand the galaxy's deepest architecture, we must confront its ghost, the dark matter halo. This invisible scaffold, weighing trillions of times more than our sun, dictates how everything within the galaxy moves. By meticulously tracking the orbits of stars and the flow of hot gas, astronomers have painstakingly mapped its gravitational influence, inferring its shadowy profile. What they find is a puzzle with implications for the entire cosmos. The observations strongly suggest the dark matter in Messier 87's core is arranged in a steep, dense cusp. Imagine a mountain that grows steeper and steeper as you climb toward the summit, the density of dark matter rising sharply all the way into the very heart of the galaxy, right down to the event horizon of the supermassive black hole. This cuspy profile is exactly what the leading theory of dark matter, called cold dark matter, predicts. In this model, dark matter particles move slowly, are unaffected by light or normal matter, and naturally sink to form these intensely concentrated central peaks as galaxies assemble. But here is where the mystery deepens. Some of the most sophisticated computer simulations of galaxy formation, when they include the complex effects of exploding stars and violent gas flows, sometimes produce a different result, a dark matter core. A core profile would look more like a flattened hilltop, a central region where the dark matter density levels off and becomes nearly constant. So which is it? Is Messier 87 a perfect example of the cold dark matter cusp, or does it secretly harbor a smoothed-out core, contradicting our best models? The answer may not lie in the models of galaxy formation alone, but in the nature of the dark matter particle itself. This discrepancy touches the fundamental question: what is dark matter actually made of? Cold dark matter particles are theorized to be heavy and slow-moving. But what if dark matter is warm? Warm dark matter would consist of much lighter, faster-moving particles. These speedy particles would have enough energy to resist collapsing into such a sharp, dense cusp, naturally washing out the center into a smoother core. Messier 87's profile could therefore be a clue to the particle's identity, a cosmic fingerprint left by the universe's most abundant yet elusive substance. There is another breathtaking possibility. Perhaps the supermassive black hole itself has sculpted its own dark matter environment. Through billions of years of complex gravitational interactions, the black hole's immense gravity could have scattered the dark matter particles, dynamically heating them and eroding a primordial cusp into a present-day core. It would be a testament to the black hole's power, not just over light and gas, but over the invisible fabric of the galaxy itself. Each precise measurement of a star's velocity in Messier 87's halo is thus a vote in a grand cosmic election, a piece of evidence that may ultimately tell us whether the universe's hidden mass is cold or warm or shaped by the monsters it helped to create. The dark matter halo may be invisible, but its gravitational handiwork is written across the sky in faint, stolen starlight, surrounding Messier 87 and spilling throughout the entire Virgo cluster is a ghostly, diffuse glow astronomers call intra-cluster light. This is not the light of distant galaxies, nor the hot X-ray glow of gas. This is the collective shine of countless individual stars, but stars that no longer belong to any galaxy at all. They are the cosmic orphans, cast adrift into the immense voids between galaxies during violent encounters over billions of years. The primary architect of this stellar sea is a process as relentless as it is destructive: galactic cannibalism. As giant galaxies like Messier 87 swing through the dense cluster, their immense gravitational pull acts like a cosmic threshing machine. During close passes or full mergers, they violently strip stars from the outer halos of their smaller neighbors and even lose some of their own, scattering them into the intergalactic wilderness. These stars do not simply vanish, they form a vast, tenuous fog that traces the history of every collision. Within this fog, specific structures emerge, faint streamers and tidal tails that act like forensic evidence. Telescopes with exquisite sensitivity have begun to map these delicate ribbons of light. One might arc from Messier 87 toward a nearby galaxy, a bridge of stolen suns marking a past gravitational tug-of-war. Another might appear as a faint, sweeping tail extending from a smaller galaxy, pointing directly back toward Messier 87 as if accusing the giant of the theft. These structures are incredibly faint, often outshone by the glare of Earth's own atmosphere, requiring special techniques to isolate their subtle signal from the overwhelming blackness of space. To understand their scale, imagine our entire Milky Way galaxy being similarly shredded. Its hundreds of billions of stars strewn across millions of light years into faint, winding rivers of light. That is the magnitude of the forces at play in the heart of the Virgo cluster. By studying the patterns and chemistry of this intracluster light, astronomers can perform a remarkable kind of cosmic archaeology. The color and metallicity of these orphan stars tell a story of their origins, whether they were ripped from the ancient, metal-poor halos of small galaxies or from the richer, inner disks of larger ones. Mapping their distribution reveals the dynamics of ancient mergers, allowing scientists to rewind the clock and reconstruct the violent dance that built the supergiant we see today. This faint glow is therefore more than just lost light. It is the permanent record of Messier 87's past feasts, a shimmering archive of galactic violence written across the void. The faint glow of orphan stars tells a story of galactic theft, but the chemistry of stars that remain can be just as revealing. Deep within the stellar swarm of Messier 87, astronomers have pinpointed a peculiar population, stars with a chemical signature that simply does not belong. These are the anomalous solar metallicity stars. Their light reveals an abundance of heavy elements, things like iron, silicon, and oxygen, that is almost identical to that of our own Sun. This fact on its surface might seem unremarkable, but in the context of a supergiant elliptical galaxy, it is a profound contradiction. A galaxy like Messier 87 is the ultimate cosmic metropolis, the product of billions of years of star formation, supernova explosions, and galactic mergers. Each generation of stars forges heavier elements in their cores and scatters them into space when they die. Over time, this process, called chemical enrichment, should make the galaxy's gas and subsequent generations of stars increasingly metal-rich. We therefore expect the stars in a giant elliptical, especially those near its core, to be super-enriched, far richer in metals than our modest Sun. Finding stars with solar-like metallicity here is like finding a simple wooden cabin in the heart of a futuristic city built entirely of polished steel and glass. They are anachronisms, relics from a different time or place. So how did they get here? One compelling narrative casts them as immigrants. During one of Messier 87's many galactic mergers, it may have consumed a smaller, metal-poor dwarf galaxy. Stars from that dwarf, born from gas that had undergone little chemical enrichment, would have a much lower metallicity. But what if the merger was not with a dwarf, but with a spiral galaxy more similar to our own Milky Way? Such a galaxy would contain a broad mix of stars, including many with solar-like abundances. As that spiral was torn apart and digested, its stars would be scattered into Messier 87's halo, leaving behind these chemical foreigners. Their presence would be a direct tracer of a specific type of meal, a galactic counterpart with a history similar to our own home. The alternative explanation requires us to rewrite the early chapters of Messier 87's own story. Perhaps the galaxy's initial burst of star formation was not uniform. Could vast clouds of pristine, metal-poor gas have lingered in the outer halo for a surprisingly long time, only collapsing to form stars well after the inner galaxy had already become enriched? These delayed stars would then have a more primitive composition, even as they now orbit within a metal-rich giant. Or maybe the enrichment process itself was less efficient than models predict, with supernova winds violently expelling enriched material out of the galaxy before it could be fully recycled into new stars, leaving behind pockets of gas that were never fully enriched. Each solar metallicity star is therefore a tiny chemical fossil. By measuring not just their iron content, but the precise ratios of many different elements, astronomers can perform a cosmic ancestry test. The pattern of elements acts like a fingerprint unique to the type of star that produced them. A signature dominated by Type II supernova, the explosions of short-lived massive stars, points to a rapid, early enrichment. A pattern rich in iron from Type I, a supernova, which take longer to trigger, suggests a more prolonged history. Matching these fingerprints to the stars in Messier 87 could tell us if they are truly native-born under unexpected conditions, or if they are strangers from a foreign galaxy, forever orbiting in the belly of the beast they helped to build. The chemical fossils of stars point to a complex history, but the present-day core of Messier 87 reveals a more immediate and startling absence. For a galaxy with such a brilliantly active jet, one would expect to find vast stockpiles of fuel near its heart, the cold molecular gas that is the essential raw material for forming new stars. Yet when astronomers search for this gas, they come up nearly empty. This is the strange case of the missing molecular reservoir. In the central regions of Messier 87, the amount of cold, dense gas detectable by instruments like the Atacama Large Millimeter Array is astonishingly low, especially when compared to other active galaxies. It is as if a colossal factory, blasting out a continuous stream of fiery products, has no visible stockroom of raw materials. This absence forces a fundamental question about the relationship between the black hole's power and the galaxy around it, a process known as active galactic nucleus feedback. The brilliant jet is the most dramatic output of this feedback, and one of its theorized roles is to regulate star formation. The classic idea is that the jet heats or disrupts surrounding gas, preventing it from cooling and collapsing into new stars. But in Messier 87, the feedback appears so efficient that it may have not just regulated the gas, but effectively removed it altogether. The jet could be acting like a cosmic blowtorch, not just warming the gas, but violently shocking it and driving it out of the central region entirely, leaving behind a sterilized zone. The energy blasting from the core might simply be too hot and too disruptive. Instead of gently compressing gas clouds to trigger star birth, it rips them apart, keeping the gas in a hot, diffuse state where molecules cannot form. There is, however, a fascinating alternative. Perhaps the cold gas is not entirely missing, but hiding in plain sight. It might exist in a form that is extraordinarily difficult for our telescopes to see, a widespread, diffuse phase rather than concentrated in dense, bright clouds. Imagine searching for water in a desert by looking only for lakes and rivers, completely missing the vast amount of water vapor suspended in the air. Similarly, the molecular gas in Messier 87 could be spread incredibly thin across a vast volume. making its collective signal too faint and smooth to distinguish from the background noise of the galaxy. This raises a critical puzzle about the efficiency of the feedback process itself. If the gas is truly gone, then the jet has been spectacularly effective at clearing its own fuel source, which might explain why the central black hole is currently in a more subdued linear state. It has, in a sense, turned down its own furnace by exhausting the local supply. But if the gas is merely diffuse, then the feedback is operating in a different mode, one where it prevents the gas from coalescing without necessarily expelling it. This would mean the raw materials for a future burst of star formation or black hole feeding are still present, just held in a kind of suspended animation by the relentless energy from the core. The lack of a significant molecular gas reservoir is therefore a silent testament to the black hole's long-term influence. It has sculpted its immediate environment not just with light and plasma, but by creating a profound emptiness, a quiet arena where its own magnificent jet is the sole performer. Even the galaxy's outer envelope of stars tells a story of violent assembly. Far from the brilliant core, the stellar halo of Messier 87 is not a smooth, featureless sphere. Instead, it is lumpy and asymmetrical, a distorted cloud of ancient suns that reveals the galaxy's true nature as a cosmic cannibal. Each subtle distortion, each overdense region or faint streamer of stars extending into the darkness is the ghost of a past meal, a smaller galaxy that was torn apart and consumed but not yet fully digested. Over billions of years, as Messier 87 plowed through the Virgo Cluster, its immense gravity acted as a celestial net, capturing dozens of smaller satellite galaxies. These victims were not instantly vaporized. Their stars were stripped away and incorporated into the giant's halo, but they did not instantly mix into a uniform soup. Instead, they remain as coherent structures like swirls of cream slowly stirring into coffee, preserving the memory of their original configuration for eons. This makes the halo an extraordinary archaeological site. By mapping these stellar lumps and streams with powerful telescopes, astronomers can perform a kind of galactic paleontology. They can count the ghosts, estimate their masses, and even trace their orbits backward in time to reconstruct a timeline of mergers. A prominent stream arcing through the northern halo might be the remains of a dwarf galaxy devoured 1 billion years ago. A faint, extended cloud of stars in the southern region could be the signature of a more recent and still ongoing act of consumption. The very shape of the halo, slightly flattened or elongated in a particular direction, might be the lasting imprint of the most massive merger in the galaxy's history, a collision that fundamentally shook the entire system and left it permanently out of round. Decoding this layered history is painstaking work. The signals are incredibly faint, requiring astronomers to subtract the smooth background glow of Messier 87's own native halo stars to reveal the subtle overdensities that shouldn't be there. It is like trying to hear a single whispered conversation in a packed, roaring stadium. But the payoff is a living history book. These asymmetries tell us that Messier 87 did not form in majestic isolation. It was built piece by piece through relentless, violent acquisition. The quiet, red glow of its halo is not a sign of serenity, but a shimmering archive of countless cosmic collisions, each one a chapter in the biography of a supergiant. The chaotic orbits of stars near the galaxy's heart tell a story of immense, hidden mass. At the very center of Messier 87, within a region just a few light years across, the stars are not moving in serene, orderly circles. Instead, they are engaged in a frenzied, random dance, zipping past one another at astonishing speeds. Astronomers measure this stellar chaos with a value called velocity dispersion, the statistical spread in the random motions of stars. In the core of Messier 87, this dispersion is extraordinarily high, meaning some stars are hurtling toward us while others race away, all at velocities that can exceed hundreds of kilometers per second. This is not a natural state for a calm stellar population. It is the unmistakable fingerprint of a monstrous gravitational presence. For decades, long before the Event Horizon Telescope produced its iconic image, this high-velocity dispersion was the primary evidence for the supermassive black hole's existence and the key tool for weighing it. The principle is elegant, like deducing the mass of an invisible planet by watching the wobble of its star. By using powerful spectrographs, astronomers could measure the tiny shifts in the light from countless stars in that central blur. Some stars' light would be shifted to the blue end of the spectrum as they shot toward Earth, others to the red as they sped away. The greater the spread or dispersion in these velocities, the more massive the object must be at the center to hold such a frenetic stellar swarm in its grip without flying apart. It was a cosmic balancing act, using the motions of the visible to infer the properties of the invisible. These measurements painted a consistent and shocking picture. There had to be an object with a mass of billions of suns crammed into a space smaller than our solar system. No collection of normal stars or dark matter could explain such a concentration. Only a supermassive black hole fit the data. This high-velocity dispersion core is therefore more than a strange dynamical feature. It is a historical landmark. It represents the moment astronomers first confidently pointed to a specific spot in the sky and said, "A monster lives there." The frantic dance of those ancient stars was our first clear message from the abyss, a gravitational whisper that prepared us for the day we would finally stare into its shadow. That frantic stellar dance is a clue to the galaxy's present, but its past may be written across the sky on a far grander scale. Astronomers are now hunting for a ghostly structure that could rewrite the entire story of Messier 87's formation, a colossal stellar stream that has so far remained just out of sight. This would not be one of the faint, local streamers we've already detected, but a monumental river of stars, a vast loop or shell wrapping around the entire galaxy, the final, fading signature of its most dramatic meal. Imagine the aftermath of a merger not with a tiny dwarf, but with a galaxy perhaps 1/4 of Messier 87's own size. Such a cataclysmic event would not just add stars, it would send titanic waves through the entire system. The smaller galaxy would be stretched into a brilliant arc by tidal forces before dissolving. Its stars scattered into a giant, looping stream that could take billions of years to fully mix and disappear. This stream would be the ultimate smoking gun, proof of a defining collision in the galaxy's relatively recent past. So why haven't we seen it yet? The challenge is one of contrast and scale. Within the dense, bright core of Messier 87, such a stream would be impossible to distinguish. But in the galaxy's outer halo, where starlight is already incredibly faint, a giant stream would be like trying to see a specific pattern in a faint, diffuse fog. Its stars would be spread over an immense area, making their collective glow perversely difficult to pick out against the black background of space and the subtle glow of the existing intracluster light. Current wide-field survey telescopes, however, are changing the game. Projects like the Vera C. Rubin Observatory are designed to map the sky with unprecedented depth and sensitivity. Their digital eyes can detect starlight so faint it pushes the limits of what is possible. The strategy is not to look for the stream as a glowing ribbon, but to hunt for the subtle, coherent motion of its stars. All the stars from the devoured galaxy would share a common orbital history, a specific velocity and direction that sets them apart from the random motions of Messier 87's native halo. By measuring the precise speeds and positions of millions of individual stars in the galaxy's outskirts, these new surveys could statistically isolate a population moving in lockstep, tracing out the shape of the stream like connecting dots in the dark. Finding such a structure would be a transformative discovery. It would provide a precise timestamp for a major merger, perhaps within the last 1 or 2 billion years, forcing us to revise the timeline of Messier 87's growth from a slow, steady accumulation to include a sudden, gargantuan leap. It would also explain many of the galaxy's other oddities in one stroke. that offset active nucleus, a natural result of a massive merger still settling down. The puzzling pockets of younger stars, fragments of gas brought in by the victim that sparked a final burst of creation. The lumpy, asymmetric halo, the obvious debris field from the collision itself. The hunt for this missing giant stream is a testament to a new era of cosmic detective work, where the faintest motions of ancient suns can reveal the most violent chapters in a galaxy's life, chapters that shape the giant we see today. The frantic stellar dance is a clue to the galaxy's present, but its past may be written across the sky on a far grander scale. Astronomers are now hunting for a ghostly structure that could rewrite the entire story of Messier 87's formation, a colossal stellar stream that has so far remained just out of sight. This would not be one of the faint, local streamers we've already detected, but a monumental river of stars, a vast loop or shell wrapping around the entire galaxy, the final, fading signature of its most dramatic meal. Imagine the aftermath of a merger not with a tiny dwarf, but with a galaxy perhaps 1/4 of Messier 87's own size. Such a cataclysmic event would not just add stars, it would send titanic waves through the entire system. The smaller galaxy would be stretched into a brilliant arc by tidal forces before dissolving, its stars scattered into a giant, looping stream that could take billions of years to fully mix and disappear. This stream would be the ultimate smoking gun, proof of a defining collision in the galaxy's relatively recent past. So why haven't we seen it yet? The challenge is one of contrast and scale. Within the dense, bright core of Messier 87, such a stream would be impossible to distinguish. But in the galaxy's outer halo, where starlight is already incredibly faint, a giant stream would be like trying to see a specific pattern in a faint, diffuse fog. Its stars would be spread over an immense area, making their collective glow perversely difficult to pick out against the black background of space and the subtle glow of the existing intracluster light. Current wide-field survey telescopes, however, are changing the game. Projects like the Messier, Rubin Observatory are designed to map the sky with unprecedented depth and sensitivity. Their digital eyes can detect starlight so faint it pushes the limits of what is possible. The strategy is not to look for the stream as a glowing ribbon, but to hunt for the subtle, coherent motion of its stars. All the stars from the devoured galaxy would share a common orbital history, a specific velocity and direction that sets them apart from the random motions of Messier 87's native halo. By measuring the precise speeds and positions of millions of individual stars in the galaxy's outskirts, these new surveys could statistically isolate a population moving in lockstep, tracing out the shape of the stream like connecting dots in the dark. Finding such a structure would be a transformative discovery. It would provide a precise timestamp for a major merger, perhaps within the last 1 or 2 billion years, forcing us to revise the timeline of Messier 87's growth from a slow, steady accumulation to include a sudden, gargantuan leap. It would also explain many of the galaxy's other oddities in one stroke. That offset active nucleus, a natural result of a massive merger still settling down. The puzzling pockets of younger stars, fragments of gas brought in by the victim that sparked a final burst of creation. The lumpy, asymmetric halo, the obvious debris field from the collision itself. The hunt for this missing giant stream is a testament to a new era of cosmic detective work, where the faintest motions of ancient suns can reveal the most violent chapters in a galaxy's life, chapters that shape the giant we see today. While we search for ghosts in starlight, other eyes see the galaxy in a different kind of glow. When viewed through the infrared-sensitive instruments of telescopes like Spitzer or the James Webb Space Telescope, Messier 87 reveals a hidden population of strange, unidentified emitters. These are not the brilliant points of X-ray sources or the smooth radio halo, but mysterious, isolated beacons of infrared light. They shine brightly at these long wavelengths, yet when astronomers point optical or radio telescopes at the exact same coordinates, they often find nothing or only a faint, ambiguous signal. These objects are cosmic phantoms, visible only in the warmth of their own hidden heat. So what could they be? The leading theory is one of cosmic shrouds. They could be incredibly dense, young star clusters still swaddled in the thick, dusty cocoons of their birth. Within these dark nurseries, thousands of new stars are igniting, but their visible light is completely absorbed by the surrounding dust. That dust, however, is warmed by the stellar radiation and re-emits the energy as a strong infrared glow, revealing the cluster's presence while hiding its true form. This would mean pockets of intense, secret star formation are still occurring in this ancient galaxy, completely invisible to our normal eyes. Another possibility pushes into more exotic territory. Some of these emitters could be regions where a supermassive star has collapsed, not into an ordinary black hole, but into a bizarre theoretical object known as a Thorne-Zitkow object. Picture a red supergiant star, one of the largest in the universe, but with a neutron star orbiting at its very core. Through complex interactions, the neutron star could spiral inward and become embedded within the giant. The result would be a stellar hybrid, a gargantuan, puffy envelope of hydrogen, fueled not by nuclear fusion in a traditional core, but by the intense heat and unusual nuclear processes on the surface of the swallowed neutron star. Such an object would have a unique and very strong infrared signature, a strange, warm giant glowing in the dark. Of course, they could also be something more mundane, yet still puzzling, like isolated clouds of dust heated by a past stellar explosion or the faint, cool glow of a single, extremely old brown dwarf that has wandered into the frame. The true frustration and fascination lie in their unidentified nature. Without a counterpart in other wavelengths, astronomers cannot easily determine their distance, size, or energy source. They are coordinates of mystery on the celestial map. Each one is a question mark written in thermal radiation, a reminder that even when we look at a galaxy with every kind of eye we possess, it still holds pockets of warmth that whisper secrets we have not yet learned to translate. The brilliant jet is a beacon of violent energy, yet it whispers where we expect a scream. In the highest energy realm of gamma rays, the most penetrating light in the universe, Messier 87 is curiously quiet. For a galaxy boasting one of the most powerful jets ever observed, its gamma-ray emission is surprisingly modest, especially when compared to other famous active galaxies like the quasar 3C273. This is a profound mismatch, a cosmic engine that roars in radio and X-rays but only murmurs in gamma rays. Why would such a powerful machine fail to produce the most extreme radiation? The answer may lie in the geometry of our viewpoint. Gamma rays are often produced most intensely when we look directly down the barrel of a jet, a head-on collision with the most energetic particles. As we've seen, the main jet in Messier 87 is likely pointed nearly toward us, but perhaps not perfectly. A slight misalignment, just a few degrees off axis, could mean we are seeing the jet's brilliant side glow in lower energies, but missing the concentrated beam of the very highest energy particles that would produce a dazzling gamma-ray signal. It is the difference between seeing the side of a lighthouse beam and staring directly into its blinding lamp. Another possibility involves the engine's internal mechanics. The process that accelerates particles to gamma-ray producing energies, often involving shock waves or magnetic reconnection within the jet, might simply be less efficient in Messier 87's specific environment. The jet could be too smooth, lacking the violent internal shocks that serve as natural particle accelerators. Or perhaps the magnetic fields within it are configured in a way that is superb at launching plasma and creating radio emission, but poor at pushing particles to the absolute limit needed for gamma-ray production. It is a powerful motor that is incredibly efficient at one task, propulsion, but less optimized for another, creating the highest energy sparks. there is also the question of obscuration. The region closest to the black hole, where the most extreme particle acceleration should occur, might be shrouded in a thick fog of lower energy radiation. The gamma rays produced there could collide with this dense sea of photons, annihilating each other in a process called pair production before the gamma rays can ever escape to be seen by our telescopes. It would be like a brilliant flash of lightning occurring deep within a thundercloud, its light completely swallowed by the surrounding storm before it can reach our eyes. This quiet gamma ray signature forces us to refine our models of how these colossal engines work. It tells us that raw power does not always translate uniformly across the spectrum. A jet can be a master of relativistic propulsion and a brilliant radio beacon, yet still operate in a regime that subtly suppresses the universe's most penetrating light. This quietness is not an absence, but a clue, a specific setting on the dial of a cosmic machine that we are only now learning to read. The faint glow of planetary nebulae should be a reliable guide through cosmic distances. When a star like our Sun reaches the end of its life, it puffs off its outer layers, creating a beautiful, glowing shell of ionized gas illuminated by the hot stellar core left behind. For decades, astronomers have used these objects as cosmic mile markers, relying on the fact that the brightest planetary nebulae in any galaxy have a remarkably consistent maximum luminosity. This creates a predictable brightness pattern called the planetary nebula luminosity function, a standard candle that allows scientists to measure how far away galaxies are. In Messier 87, however, this reliable tool begins to behave strangely. The distribution of these glowing shells shows an unusual anomaly, a specific kink or deficit in the expected number of nebulae at certain brightness levels. It is as if a standard ruler used across the universe suddenly has a few centimeters missing when applied to this particular giant. This mismatch forces a deep look into the life and death of stars within this unique environment. The standard model assumes a typical population of aging, Sun-like stars will produce a predictable range of planetary nebulae. But in Messier 87, the stars that are dying to create these nebulae might be fundamentally different. One possibility is a unique population of progenitor stars. Imagine the stellar population of this cannibalistic giant. Through its many mergers, it may have acquired an overabundance of stars from a specific mass range, perhaps slightly heavier or lighter than the solar mass stars we typically associate with planetary nebulae. These stars would die differently, leaving behind cores of different temperatures and ejecting envelopes of different masses, which would directly affect the final brightness of the nebula. The anomaly could be the collective signature of a foreign population of dying stars, all sharing a strange family history. The other compelling explanation lies in the complex chemistry of the nebulae themselves. The brightness of a planetary nebula depends heavily on the chemical composition of the gas being lit up. Elements like oxygen and neon are particularly efficient at converting ultraviolet light from the central star into the visible glow we see. In a galaxy as chemically enriched and complex as Messier 87, the interstellar medium that these dying stars expel their material into is not pristine. It is already polluted with heavy elements from countless past supernovae. This pre-enriched gas could alter the cooling properties and the emission lines of the resulting nebula in subtle ways, making some appear dimmer or brighter than the simple models predict. It is like trying to predict the color of a flame by knowing only the fuel, but forgetting that the air itself might be filled with different gases that change the hue and intensity of the burn. This anomaly is more than a technical hiccup in distance measurement. It is a direct probe into the life cycles of stars within an extreme galactic ecosystem. The quiet, glowing shells of dying suns are telling us that the rules of stellar death are not universal. They are shaped by the history of the galaxy itself, by its violent mergers and its polluted environment. Each faint planetary nebula in Messier 87 is therefore a final message from a star, a message that carries not just information about distance, but a coded story about where that star was born, what it was made of, and the strange galactic home in which it spent its final days. The faint ghosts orbiting this giant are not merely streams of stars, but entire galaxies cloaked in shadow. Circling Messier 87 are some of the universe's most enigmatic objects, ultra-diffuse galaxies. These are not the bright, compact dwarfs one might expect. They are sprawling, ghostly structures as large in diameter as our own Milky Way, yet containing only about 1% of its stars. Picture a city the geographic size of New York, but with only the streetlights of a small town, a vast, dim expanse where light barely clings to the darkness. The most famous of these near Messier 87 is Dragonfly 44, a satellite so diffuse it was only discovered in 2015 because it was almost perfectly invisible. Its stars are so few and so spread out that the galaxy is literally see-through, offering almost no resistance to the light from more distant galaxies behind it. This creates a profound mystery of survival. How can such a fragile, gossamer structure endure in the violent gravitational neighborhood of a supergiant like Messier 87? The tidal forces here should shred a galaxy with such weak self-gravity, stretching it into a stream of stars to be consumed by the giant. The fact that Dragonfly 44 and others like it still exist suggests they possess a hidden source of strength. The leading theory points to an overwhelming presence of dark matter. Observations indicate these ultra-diffuse galaxies might be dominated by invisible mass, with dark matter making up perhaps 99% of their total substance. This would give them a gravitational anchor, a deep, unseen well of gravity that holds their sparse stars in place despite the external pull. They would be dark matter fortresses wearing only a veil of stars. This raises the question of their origin. Are they failed galaxies? In this scenario, they formed in the early universe with vast halos of dark matter. But for some reason, perhaps because they were in a cosmic void with little gas, they never managed to form many stars. They are the cosmic equivalent of a fertile field that never got seeded, all potential with minimal yield. The alternative is a story of violent transformation. Perhaps they were once normal dwarf galaxies, rich with stars, that ventured too close to Messier 87. The giant's tides could have stripped away the majority of their stars and gas, leaving behind only the dense, dark matter-dominated core and a faint haze of the original galaxy's most tightly bound stars. What we see today would be the stripped, skeletal remains of a galaxy, its bright flesh torn away to reveal the dark bones beneath. Each ultra-diffuse satellite is therefore a cosmic paradox, a giant in size that is a dwarf in light. Their continued existence near Messier 87 challenges our understanding of galaxy formation and survival, forcing us to ask whether the true architecture of a galaxy is written not in stars, but in the invisible scaffolding that holds them, a scaffolding that can sometimes stand almost completely alone. The ancient globular clusters of Messier 87 reveal their history not just in their light, but in their color. When astronomers plot the colors of these 12,000 stellar cities, a striking pattern emerges. They do not form a smooth spectrum from blue to red, but instead split cleanly into two distinct families, a phenomenon known as the color bimodality. There is a clear population of blue globular clusters and a separate, equally distinct population of red ones. This simple division is a profound clue, a cosmic fingerprint left by two completely different chapters in the galaxy's violent life. The color of a star cluster is a direct indicator of its chemical makeup. Blue clusters are metal poor, meaning they contain very low amounts of elements heavier than hydrogen and helium. Their stars are ancient, pristine, and forged from the raw material of the early universe. The red clusters, in contrast, are metal-rich. Their stars are sprinkled with the heavier elements cooked in the cores of earlier stellar generations and scattered by supernova explosions. This bimodality tells us that Messier 87 did not build its cluster system in one event, but through at least two separate epic processes. The blue metal pore clusters are likely the galaxy's original inhabitants or its earliest acquisitions. One possibility is that they formed in situ, condensing from the primordial gas cloud that collapsed to form Messier 87 itself over 12 billion years ago. Another is that they were stolen, the intact globular cluster systems of the first dwarf galaxies this giant cannibalized in its youth. In either case, they represent the ancient foundational layer of the galaxy's structure. The red, metal-rich clusters tell a story of later, more violent construction. These clusters almost certainly formed during the colossal, gas-rich mergers that built the galaxy's main body. When two sizable spiral galaxies, each already enriched with metals from billions of years of star formation, slammed together, the shockwaves would have compressed vast reservoirs of gas. This triggered intense fireworks like bursts of new star formation, and within those maelstroms, new globular clusters were born. These second-generation clusters formed from pre-polluted gas, so their stars were born metal-rich from the start, giving them their distinctive red hue. Each red cluster is therefore a fossilized timestamp of a specific catastrophic merger. The very presence of two clear color groups forces us to see Messier 87 not as a monolithic entity, but as a layered archaeological site. The blue clusters are the bedrock, the red clusters are the strata deposited by later cataclysms. By counting the ratio of blue to red clusters and mapping their locations, astronomers can begin to reconstruct the sequence of events that assembled this galactic giant. It is a history written not in words, but in the subtle shades of starlight from billions of ancient suns. The color of ancient starlight tells one story, but the galaxy holds another, written in delayed reflections. While we have not yet captured one in Messier 87, the potential exists to witness a ghostly replay of its most violent moments through a phenomenon called a light echo. Imagine a colossal explosion near the supermassive black hole, a titanic flare from the jet, or the brilliant death scream of a star being torn apart in a tidal disruption event. In that instant, a flash of intense radiation blasts outward in all directions at the speed of light. The direct light from that flash reaches us 55 million years later, registering as a single, brilliant spike in our telescopes. But the story does not end there. That initial flash also races outward until it slams into vast, distant clouds of interstellar dust orbiting far from the core. The dust does not absorb the light completely, it scatters it, reflecting it toward us like a cosmic mirror. Because this reflected light takes a longer, indirect path, it arrives at our telescopes months, years, or even decades after the direct flash. We would see the main event, and then, slowly, a luminous wave would appear to expand outward from the core, a growing shell of light that is not new energy but an echo of the old. Observing such an echo would be like watching a historical documentary of the explosion itself, but in slow motion and in 3 dimensions. As the echo expands, it illuminates different parts of the dust clouds that lie at different distances from the black hole. By meticulously mapping the changing shape and brightness of this expanding shell, astronomers could perform a kind of cosmic tomography. They could reconstruct the 3-dimensional structure of the dust clouds themselves, revealing hidden rings, spirals, or cavities in the galaxy's interstellar medium that are otherwise invisible. More profoundly, the echo's light would carry a spectrum, a chemical fingerprint of the original event. By comparing the echo's spectrum to the spectrum of the initial flash, scientists could study how the light has changed after interacting with the dust, revealing the dust's composition and grain size. It would also allow them to watch the evolution of the explosion's aftermath from a new angle, literally seeing the event reflected off different surfaces. The hunt for such an echo in Messier 87 is a patient one. It requires monitoring the galaxy's core not just during a flare, but for years afterward, looking for subtle, expanding rings of infrared or optical light that have no other explanation. Finding one would transform a single data point, a brief flare in our records, into a rich multi-year documentary. We would no longer just know that an explosion happened. We could watch its aftermath unfold across the galactic stage, seeing its light paint the hidden structures of the galaxy long after the central fire has faded. It would turn the galaxy itself into a vast recording device, where every dust cloud is a page waiting to be illuminated by the echoes of ancient cataclysms. The brilliant knots in that jet hold a secret that seems to break the universe's ultimate speed limit. Detailed observations over decades reveal something impossible. These glowing hotspots appear to move across our line of sight at speeds greater than light itself. We call this superluminal motion, and it is one of the most startling and well-understood illusions in all of astrophysics. It does not mean Einstein was wrong. It means our perspective is playing a profound trick on us. To understand it, picture a single bright knot of plasma blasted from the black hole at 99.9% the speed of light, and imagine it is aimed almost directly at Earth. As this knot travels, it emits light continuously. The light it emits at a point closer to us has less distance to travel than the light it emitted just a moment earlier from a point slightly farther away. If the knot is coming almost straight toward us, the later light can arrive at our telescopes almost simultaneously with the earlier light, making it seem as though the knot crossed a vast distance in almost no time at all. From our vantage point, it appears to have moved faster than light, a cosmic sleight of hand born from geometry and relativity. The effect is like watching a distant water skier at night, their headlight cutting across the lake. If they are skiing almost directly toward you, the sideways motion of their light on the water can appear to move faster than the skier themselves, creating an exaggerated, impossible speed across your field of view. In Messier 87, careful tracking of these knots has allowed astronomers to turn this illusion into a precision tool. By measuring the apparent superluminal speed, they can calculate the jet material's true, breathtaking velocity and, crucially, the exact angle at which the jet is pointed toward us. The math reveals the jet is likely inclined by only about 17 degrees from our line of sight, which is why the effect is so pronounced and why the jet appears so brilliantly beamed. This precise measurement solves multiple puzzles at once. It confirms why we see such a dazzling jet and such a faint counterjet, and it tells us the raw power required to accelerate matter to such velocities. Every knot racing across the sky, seemingly defying physics, is therefore a celestial speedometer and protractor, its impossible motion giving us the exact coordinates and power settings of the black hole's most violent output. The silent core extends to the stars locked in deadly dances. In the bustling spiral arms of star-forming galaxies, brilliant X-ray beacons flash like cosmic lighthouses. These are the bright X-ray binaries where a normal star orbits a compact stellar corpse, a neutron star or black hole. As the dense object strips gas from its living companion, the stolen material spirals in, heats to millions of degrees, and shines with fierce X-ray light. In a galaxy like our Milky Way, such systems are expected, even common. Yet in the vast stellar metropolis of Messier 87, these brilliant duos are strangely, almost eerily, absent. The galaxy's population of bright X-ray binaries is far lower than models predict, creating a quiet zone where violent stellar partnerships should thrive. This scarcity forces a deep look into the life and death of stars in an environment devoid of new birth. The key lies in the age of the stellar population. Messier 87 is a retirement home for ancient stars. The brilliant, massive stars that live fast, die young, and leave behind the neutron stars and black holes needed for these binaries simply no longer exist here. They perished billions of years ago. The compact objects that remain are relics of that distant past, and they now orbit the long-lived, low-mass stars that fill the galaxy. These older stellar pairs are typically wider, more sedate, and produce only a faint trickle of X-rays, if any at all. This much is expected, but the extreme scarcity of even the few bright binaries that should exist points to a more complex evolutionary history. It tests our understanding of how binary star systems behave over cosmic time in a dense, chaotic environment. One possibility is a process called dynamical friction. Over billions of years, as binary systems orbited through the crowded core of Messier 87, gravitational interactions with countless passing stars could have gradually tightened their orbits. This might have caused the binary partners to merge long ago, removing the very systems that could have later become bright X-ray sources. The galaxy's dense stellar environment may have effectively sterilized itself of potential binaries through slow gravitational attrition. Another, more dramatic idea involves the black hole's influence. The same violent gravitational encounters that can create hypervelocity stars could also disrupt binary systems before they ever have a chance to become bright X-ray emitters. A close pass to the central supermassive black hole or its possible companion could tear a binary apart, flinging the compact object away on a new trajectory and leaving the normal star to wander alone. In this scenario, the core of Messier 87 is not just a quiet place. It is a destructive one, actively dismantling the stellar partnerships that other galaxies nurture. This lack of bright X-ray binaries is therefore a negative observation that speaks volumes. It tells us that the story of binary star evolution is not universal. The rules change inside a giant elliptical galaxy where time, density, and a central monster have had billions of years to reshape stellar relationships. The silence in the X-ray sky above Messier 87 is not an emptiness, but a record of countless quiet endings, of partnerships dissolved or merged long before they could ever flare into brilliant, violent light. Drifting in the vast, dark ocean between galaxies are the loneliest ghosts of all. These are not the collective glow of intracluster light, but individual, pinpoint beacons, the intracluster planetary nebulae. Each one is a dying sun that has been completely severed from its home galaxy, floating freely in the immense void of the Virgo Cluster. They are the ultimate cosmic exiles, and their faint greenish glow tells a story of violent ejection on a scale we are only beginning to map. Think of a planetary nebula as the final glowing breath of a star like our own sun. For billions of years, such a star lived a quiet life, bound by gravity to its galactic home, perhaps in the outer halo of Messier 87 or one of its many satellite galaxies. Then, during a close gravitational encounter, a galactic merger or a near miss, the star found itself on the wrong side of a cosmic tipping point. The tidal forces were just strong enough to pluck it from its orbit, like a pebble flicked from a spinning wheel, and fling it out into the intergalactic abyss. It carried on with its life cycle, unaware it was now an orphan. Millions of years later, as it reached its end, it puffed off its outer layers. That expanding shell of gas, illuminated by the star's hot core, now shines as a planetary nebula. But there is no galaxy in its background, no stellar city to call home. It glows in perfect isolation, a single ephemeral flower blooming in the deepest desert. Their isolation is precisely what makes them such powerful scientific tools, because these nebulae are such distinct, bright points against the featureless dark. Astronomers can use powerful spectrographs to measure their motion with incredible precision. By analyzing the Doppler shift in their light, scientists can determine exactly how fast each one is moving and in what direction. This turns a field of these orphaned nebulae into a swarm of test particles, each one tracing the invisible gravitational field of the entire Virgo cluster. Imagine releasing thousands of glowing buoys into a dark, turbulent sea. By tracking how each buoy drifts and accelerates, you could map the hidden currents and depths below. In the same way, the motions of intracluster planetary nebulae allow astronomers to chart the gravitational potential of the cluster, weighing the total mass both dark and visible. that governs the motion of everything within it, from giant galaxies to these solitary stars. More directly, they are the smoking gun of the stellar stripping process we have discussed. Every single intracluster planetary nebula is direct forensic evidence of a star that was ripped from a galaxy. By studying their numbers and distribution, astronomers can quantify the ferocity of this process. Are they evenly scattered, suggesting a long, steady history of tidal stripping? Or are they concentrated in specific streams and clouds, pointing to the debris trails of particular, recent galactic collisions? Their light provides a chemical fingerprint as well, telling us which type of galaxy they were stolen from, whether it was a metal-rich giant like Messier 87 or a metal-poor dwarf. They are not just lost stars, they are witnesses with testimony, their velocity and composition recounting the exact moment and manner of their violent expulsion. Finding them, however, is a monumental task of cosmic needlework. Their signal is incredibly faint, and they must be distinguished from the billions of foreground stars in our own Milky Way and the distant, unresolved galaxies in the background. It requires painstaking surveys that scan the same patch of sky between the major galaxies of the Virgo Cluster, looking for the specific, telltale emission of doubly ionized oxygen that gives these nebulae their characteristic green hue in specialized filters. Each confirmed detection is a triumph, adding another day to point to the map of the cluster's hidden skeleton. So the next time you see an image of the Virgo cluster with its majestic galaxies suspended in the dark, remember that the emptiness between them is not truly empty. It is sprinkled with these lonely, fading embers, the final size of stars that were thrown from their homes. They are more than just beautiful cosmic relics. They are the most sensitive tracers we have of the gravitational wars that shape the universe, and a poignant reminder that even in the grandest structures, individual stories of exile and transformation are forever written in light. Even the galaxy's searing atmosphere holds frozen scars. Within the multimillion-degree X-ray glow that envelops Messier 87, astronomers have discovered something that seems impossible: sharp, knife-edge boundaries slicing through the superheated gas. These are called cold fronts, and the name itself is a cosmic contradiction. The gas on either side is unimaginably hot, but one side is distinctly colder and denser than the other, creating a stark temperature cliff millions of light years long. This is not a shock wave, the violent, supersonic blast from an explosion. A shock would heat and mix everything it passed through. Instead, this is a contact discontinuity, a stable, lingering interface where two distinct bodies of gas press against each other without merging, like oil floating on water. Imagine the galaxy's vast halo of hot gas as a cup of coffee that has been gently swirled. The liquid inside doesn't instantly become uniform. It develops subtle layers and currents as the denser, cooler fluid sloshes against the sides. On a galactic scale, this sloshing is caused by a profound gravitational jolt, most likely the recent flyby or merger with another sizable galaxy. This disturbance sets the entire ocean of hot gas into a slow, ponderous motion. The denser, cooler gas from the galaxy's inner regions begins to slide outward, plowing through the hotter, more diffuse gas of the outer halo. Because this motion is subsonic, relatively slow and smooth, it doesn't create a destructive shock. Instead, it shepherds a coherent mass of gas, maintaining its identity as it moves, its leading edge forming that sharp, cold front. The persistence of these razor-sharp edges over hundreds of millions of years is a revelation. It tells us that the hot intergalactic medium, often thought of as a chaotic, turbulent soup, can in fact behave with a strange, laminar elegance. Magnetic fields threading the gas likely play a crucial role, acting as a protective sheath around the colder cloud, suppressing turbulence and preventing it from dissolving into the hotter surroundings. It's a magnetic cocoon preserving a fossil of the galaxy's inner atmosphere as it voyages outward. Finding and mapping these fronts is like reading the ripples in a pond long after the stone has sunk. By analyzing their curvature and location, astronomers can work backward. They can estimate the direction and magnitude of the initial disturbance, asking what hit this galaxy and when. The cold front becomes a forensic tool, a dynamic fossil that records not just the existence of a past collision, but its precise dynamics. It reveals that the aftermath of galactic violence isn't always fire and fragmentation. Sometimes it's a slow, majestic slosh, writing the history of the impact in temperature gradients that last for cosmic epochs. The violent sloshing of hot gas is a grand, slow-motion echo, but the debris from galactic collisions can sometimes coalesce into something entirely new. On the outskirts of Messier 87, astronomers have identified a peculiar, compact object that defies easy classification. It appears as a dense knot of stars and a surprising amount of cold gas, but it isn't a typical globular cluster, and it's far too small and irregular to be a traditional dwarf galaxy. This strange clump is a prime candidate for one of the universe's most fascinating second-generation structures, a tidal dwarf galaxy. This concept turns our understanding of galaxy formation on its head. We are taught that galaxies are born from the top down, condensing within vast halos of dark matter in the early universe. A tidal dwarf galaxy proposes the opposite, a bottom-up birth from the wreckage of a cosmic crash. Picture the aftermath of two large spiral galaxies merging. As they tear each other apart, colossal tidal forces pull out immense streams of gas and stars like stretching cosmic taffy. Within these streams, denser pockets of gas can collapse under their own gravity. This isn't primordial gas from the dawn of time. It is enriched material that has already been processed through generations of stars full of heavy elements. If the conditions are just right, this recycled debris can ignite a burst of star formation and bind itself into a gravitationally independent object, a new galaxy born from the ruins of the old. What makes this candidate near Messier 87 so compelling is its possession of that cold gas. Traditional dwarf galaxies orbiting giants are usually gas-poor, having had their fuel stripped away by tidal forces or blown out by supernova long ago. This object, however, holds onto a reservoir. This suggests it formed recently from gas that was ripped out in a relatively recent merger and hasn't had time to be stolen back or evaporated by the hostile environment. Its stars, if we could measure them in detail, would likely show a metal-rich signature, confirming they were forged from pre-polluted material, not from the pristine hydrogen of the early cosmos. Confirming this object as a true tidal dwarf would be a landmark discovery. It would prove that galaxy formation is not a relic process confined to the ancient past, but an ongoing creative force. It would show that the universe can still build new galactic islands today, not from the dark matter scaffolding of the cosmic web, but from the sheer chaotic energy of destruction. This candidate is a test of resilience. Can a newborn galaxy, lacking the protective deep gravity well of a dark matter halo, survive for long in the gravitational maelstrom around a supergiant? Or is it a temporary cosmic eddy destined to be pulled apart and absorbed in its turn? Finding the answer means studying its motion to see if it's on a bound orbit or an escape trajectory, and mapping its internal gravity to see if it's truly held together by its own stars and gas, or if it's just a transient clump soon to dissolve. This strange knot of light is therefore a question about origins. Are all galaxies born from darkness, or can they also be born from light, from the brilliant, scattered debris of their ancestors? The invisible architecture of the galaxy is written in twisted light. When radio waves from that brilliant jet travel through space, they do not journey through a perfect vacuum. They pass through a diffuse sea of hot, magnetized plasma, the very gas that fills the space between galaxies in the Virgo Cluster. This journey leaves a distinct fingerprint on the light, a phenomenon called Faraday rotation. Imagine a radio wave as a vibrating string. Its vibrations can be oriented in a specific direction, a property we call polarization. As this polarized wave moves through a magnetized plasma, its orientation slowly twists like a screw turning. The amount of this twist, the Faraday rotation measure, depends on two things: the strength of the magnetic field along the line of sight and the density of electrons it passes through. By meticulously mapping this rotation across the jet and the surrounding halo, astronomers have created a chart of the cluster's hidden magnetic skeleton. What they've found is not a simple, orderly pattern. The Faraday rotation measures around Messier 87 are a chaotic tapestry of strong and weak twists, a complex and deeply asymmetric map. This tells us the magnetic field enveloping the galaxy is not a neat set of lines radiating from the core. It is a turbulent, tangled web, woven on a scale of hundreds of thousands of light years by the violent motions of galaxies and the powerful outflows from black holes over billions of years. This field, though invisible, is a crucial player in the galaxy's life story. It acts as a cosmic buffer, influencing how the hot cluster gas moves and how effectively it can cool. It can trap high-energy particles, shaping the faint radio halo we see. Most importantly, it regulates feedback. The magnetic field channels and confines the energy from the black hole's jet, helping to shape those colossal X-ray cavities and determining how far the heating influence extends. A strong, tangled field can stifle turbulence, allowing the hot gas to settle into the sharp, cold fronts we observe. Yet, despite its importance, we understand this magnetic architecture poorly. Is it primordial, a relic from the universe's infancy stretched and amplified by cosmic flows? Or is it forged anew in the shocks and shears of galactic collisions and black hole outbursts? Each twisted path of a radio wave through this magnetized fog is a clue, a single thread in a tapestry we are only beginning to trace, revealing that the true shape of a galaxy is sculpted not just by gravity, but by the silent, pervasive force of magnetism. The magnetic tapestry is woven with threads of unimaginable power. Beyond even the brilliant gamma rays we have discussed lies a realm of truly staggering energy, the domain of tera-electronvolt emission. This is light with a punch, each individual photon carrying over 1 trillion times the energy of visible light. Telescopes like MAGIC and HESS do not see this light directly. Instead, they detect the faint, fleeting blue flashes created when these monstrous gamma rays slam into Earth's upper atmosphere. The fact that Messier 87 is a bright source in this extreme band is a revelation in itself, but the real mystery lies in its behavior. This titanic emission does not shine with a steady, stately glow. It flickers violently and unpredictably, flaring up and fading away over mere days. This timescale is the key to a profound constraint. Light can only travel a finite distance in a day. For the entire emission region to brighten or dim in such a short period, its physical size must be smaller than the distance light can travel in that same time. This forces an astonishing conclusion. The engine producing this tera-electronvolt light is incredibly compact, crammed into a region perhaps no larger than our own solar system. Given the scale of the jet, which stretches for thousands of light years, this means the acceleration site for these ultimate particles must be situated extraordinarily close to the black hole itself, likely within the chaotic inner regions of the jet's launch zone or the turbulent swirl of the accretion disk. This is the universe's most powerful natural particle accelerator operating at its limit. The processes at work here are beyond anything we can replicate on Earth. We are likely witnessing particles, perhaps protons or electrons, being whipped to near light speed by colossal shock waves or unimaginably strong magnetic fields that snap and reconnect in a torrent of energy conversion. Each tera-electronvolt photon we detect is a messenger from this maelstrom, a direct signal from the edge of the event horizon where gravity and magnetism conspire to hurl matter into the abyss and light into the void. This rapid variability is a siren call to theorists, challenging them to explain how such efficient acceleration can occur in such a confined, brutal space. It suggests the black hole's environment is not just powerful, but exquisitely tuned to transform gravity and spin into the most energetic radiation the cosmos can produce. Yet for all the violence of its central monster, the true scale of death in this galaxy is measured in quiet, invisible multitudes. The supermassive black hole is the king, but its court is filled with millions of silent nobles, the stellar mass black holes. Each one is a tombstone, the collapsed core of a massive star that burned through its fuel billions of years ago in a spectacular supernova explosion. At this distance, we cannot see a single one of them directly. A solitary black hole with a few times the mass of our Sun, drifting in the dark, emits no light of its own. It is only visible if it is actively feeding, pulling gas from a companion star in a brilliant X-ray binary. And as we've seen, those are strangely scarce in Messier 87. So how do we know they are there, let alone that they number in the tens of millions? The answer lies not in spotting the tombstones, but in counting the graves. Astronomers use a powerful form of cosmic statistics, inferring the population from the properties of the stars that are visible. They begin with what they can see and measure, the total starlight of the galaxy's central bulge, its color and its spectrum. This light tells a detailed story about the types of stars present, their masses and their ages. From this, scientists can reconstruct the galaxy's star formation history. They can calculate how many massive stars, those behemoths 8 or more times heavier than our Sun, were born over Messier 87's long lifetime. The physics of stellar evolution is remarkably consistent. We know with great certainty that every single one of those massive stars ended its life in a core collapse supernova. And from observations in our own galaxy, we know the rough fraction of those explosions that leave behind a black hole versus a neutron star. It becomes a simple yet staggering calculation. Take the estimated number of massive stars that have lived and died. Apply the percentage that become black holes. The result is a census of the dead. For a supergiant elliptical like Messier 87, which formed the bulk of its stars in a frenzied burst over 10 billion years ago, that number soars into the tens of millions. These black holes are not evenly distributed. They will be concentrated in the galaxy's dense central bulge, where star formation was most intense in its youth. They swarm around the supermassive black hole like a dark gravitational mist, the legacy of that ancient fiery period of creation. Their collective presence, though invisible, has subtle gravitational effects that can be inferred. They contribute to the high-velocity dispersion of stars in the core, adding to the chaotic dance driven by the central monster. They also play a long-term role in a process called dynamical friction. As stars and other black holes orbit through this dense swarm, their gravitational interactions slowly drain energy, causing heavier objects like these stellar black holes to gradually sink toward the very center over billions of years. This process may help feed the supermassive black hole and could even contribute to the formation of a dense cusp of dark objects right at the galaxy's heart. So while we cannot point to a single pinpoint of darkness and say there is one, we can be utterly confident of the silent multitude. They are the dark echoes of the galaxy's most brilliant, short-lived stars, a vast and unseen population that shapes the core's dynamics from the shadows, a gravitational memory written in absence. Amidst the ancient red glow of this galactic giant, a splash of unexpected color stands out like a sapphire in a field of rust. This is the strange blue blob, a compact and brilliant region where the light is not the cool red of old stars, but the fierce, hot blue of stellar youth. Its very color is a declaration of anomaly, a signal that within this gas-poor, quiescent environment, a pocket of vigorous star formation is either happening right now or happened so recently that the stellar embers are still blazing. Finding such a region in Messier 87 is like discovering a lush green oasis in the middle of a vast, sun-baked desert where rain hasn't fallen for 1 billion years. It simply shouldn't be there, and its existence forces a fundamental question about the source of its fuel. The first possibility is a story of internal, unlikely creation. Could this blue blob be an example of in situ star formation, new stars being born from the galaxy's own meager resources? For this to happen, a significant reservoir of cold molecular gas, the raw material for stars, would have had to somehow condense within Messier 87's hostile halo. Perhaps a rare, perfect storm of conditions allowed a pocket of the hot, X-ray emitting gas to cool rapidly and collapse, overcoming the heating influence of the central black hole's outbursts. This would be a fragile and fleeting event, a single spark managing to catch in a damp, windy environment. The stars born from such a process would likely be metal-rich, carrying the chemical signature of Messier 87's long history of enrichment, and they would be isolated, with no surrounding stream of older stars to call family. The alternative explanation is one of cosmic capture. The blue blob may not be a native feature at all, but the bright, disrupted heart of a dwarf galaxy in its death throes. Imagine a small, gas-rich satellite galaxy, perhaps a faint, irregular dwarf, on a doomed orbit. As it was pulled into Messier 87's immense gravitational well, the violent tidal forces began to strip away its outer stars and dark matter, leaving its dense, gas-packed core exposed and vulnerable. This compression of the remaining gas could have triggered a final, desperate burst of star formation, a brilliant last gasp before the dwarf is completely shredded and assimilated. In this scenario, the blue blob is a temporary celestial trophy, the glowing core of a galaxy being consumed. We would be witnessing the act of cannibalism in real time, with the victim shining brightly in its final moments. Distinguishing between these two origins requires a forensic analysis of the blob's light. Astronomers would look for the subtle motions of its stars. Are they moving in a chaotic, random way, suggesting they were born in place from a collapsing cloud? Or do they share a coherent, streaming motion, all moving together in the same direction like a school of fish, which would be the hallmark of a captured system being pulled apart? They would also analyze its chemical makeup. Does it have the high metallicity expected from gas recycled through many generations of stars in a giant elliptical? Or does it show a more primitive, metal-poor signature, indicating it came from a smaller, less evolved galaxy? The lifespan of this blue region is another clue. If it is a true starburst, the massive, blue stars it contains are cosmic mayflies, destined to explode as supernova within a few tens of millions of years. Their violent deaths will blast the remaining gas away, leaving behind only a faint cluster of longer-lived stars that will quickly redden and fade into the galactic background. The blob would be a transient flare of youth, a brief contradiction in the galaxy's long, quiet history. If, however, it is the core of a captured dwarf, it might persist a little longer, its structure gradually dissolving as its stars are scattered into Messier 87's halo. Either way, this splash of blue is a punctuation mark in the galaxy's biography, a brief, brilliant clause that tells of either a miraculous internal rebirth or a violent act of galactic consumption still unfolding before our eyes. Gravity can sculpt the cosmos into a hall of mirrors. The sheer mass of Messier 87, trillions of suns worth of stars, gas, and dark matter, warps the very fabric of space around it. This curvature acts like a colossal, imperfect lens, bending the paths of light rays that pass nearby. When a distant, faint galaxy lies directly behind this massive foreground object from our perspective, its light is distorted and magnified. Instead of seeing a single, sharp galaxy, we might see multiple, stretched and smeared images of it, arranged in a faint arc or even a complete ring encircling the giant. This phenomenon is a gravitational lens, a direct prediction of Einstein's general relativity, and Messier 87 is a prime candidate to host such a spectacle. While enormous galaxy clusters are the most powerful cosmic lenses, often producing spectacular giant arcs, a single galaxy like Messier 87 creates a subtler effect. Its lensing power is weaker, so the distorted images of background galaxies are fainter and harder to spot against the galaxy's own brilliant glow. They would appear as delicate bluish arcs or multiple tiny smudges of light embedded in the outer halo, signatures of a universe far more distant seen through a gravitational telescope. Finding these lensed candidates is a painstaking task of cosmic subtraction. Astronomers must first model and remove the smooth, overwhelming light of Messier 87 itself, then scour the residual image for these faint, coherent shapes that shouldn't be there according to normal geometry. The scientific payoff for spotting even one such lensed arc, however, is immense. It provides a completely independent way to weigh the galaxy. The degree of distortion, the separation and brightness of the multiple images depends precisely on the total mass of the lensing object, the mass enclosed within the arc's radius. This measurement includes everything: stars, gas, and most importantly, the invisible dark matter halo. It is a pure gravitational scale, unaffected by the type of matter creating the pull. By comparing this lensing mass to the mass estimated from the motions of stars or hot gas, scientists can check for consistency in our models of dark matter distribution. A discrepancy could reveal if the dark matter halo is more or less concentrated than we think, or if our understanding of the galaxy's three-dimensional shape is flawed. Furthermore, these lensed arcs are more than just mass probes. They are windows to the infant universe. The background galaxies being lensed are typically at extremely high redshift, meaning their light has been traveling for over 10 billion years. Without the gravitational lens, they would be far too faint and small for our telescopes to study in any detail. The lens magnifies them, acting as a natural telescope built by gravity itself. Through these cosmic lenses, astronomers can peer into the conditions of the early cosmos, studying the shapes, sizes, and star formation rates of galaxies when the universe was only a fraction of its current age. Each faint arc around Messier 87 would therefore be a double discovery: a precise measurement of the giant's hidden mass in the foreground, and a magnified, detailed glimpse of a galaxy under construction in the distant background, all written in the same bent line of light. That central engine's power seems to defy its own internal mechanics. One of the most surprising revelations about the supermassive black hole M87 star is not its immense mass, but what may be missing: a sense of dizzying spin. Current estimates pieced together from the structure of its jet and the shape of its shadow suggest this cosmic monster may be rotating relatively slowly. This finding stands in stark contradiction to a fundamental expectation. For decades, astrophysicists have theorized that a black hole's ferocious spin is the primary battery for launching those magnificent relativistic jets. The logic is compelling, rooted in Einstein's frame-dragging effect. A spinning black hole twists the very fabric of space-time around it, like a spinning spoon in a cup of honey. This twisted space can drag magnetic fields anchored in the accretion disk, winding them into a powerful coil that acts like a cosmic slingshot, flinging material out along the poles at nearly light speed. A fast spin should mean a more powerful, more stable jet. M87's brilliant 5,000 light-year-long beam certainly suggests immense power, so a slow spin presents a fascinating paradox. How can a seemingly lazy spinner produce such a focused torrent of energy? This puzzle forces us to reconsider two major aspects of the black hole's life story: its diet and our theories. The first explanation is a story of a chaotic, messy upbringing. Black holes gain spin primarily by feeding, but the direction of the incoming material is crucial. If gas falls in from a consistent direction, like water swirling down a drain, it transfers its angular momentum to the black hole, spinning it up. But what if M87 star grew not from a steady, orderly diet, but through a series of violent, random snacks? Imagine the black hole consuming many small satellite galaxies or gas clouds over billions of years, each one approaching from a different, random angle. One meal might spin it clockwise, the next counterclockwise. Over time, these conflicting feeds could cancel each other out, leaving the black hole with a net spin that is modest or even nearly zero. Its immense mass would then be a testament to quantity, not consistency, built from a chaotic buffet that left it powerful but not particularly dizzy. The second possibility is far more profound. It suggests our fundamental understanding of how jets are launched might be incomplete or even wrong. Perhaps the black hole's spin is not the sole driver we thought it was. Could the immense power instead be extracted directly from the magnetic fields in the accretion disk itself, independent of the black hole's rotation? Or maybe the rotational energy of the inner accretion disk just outside the event horizon is sufficient to power the jet, even if the black hole at the very center is not spinning rapidly. This would mean the jet is like a powerful engine bolted onto a flywheel, drawing its energy from the whirl of matter just outside the point of no return, rather than from the vortex of the singularity itself. There is also the tantalizing possibility that we are simply misreading the clues. Measuring a black hole's spin from 55 million light-years away is an indirect and incredibly difficult art. The estimates rely on complex models that link the jet's properties and the shadow's asymmetry to the spin parameter. If our models of the accretion flow or the magnetic field geometry are slightly off, our spin estimate could be off as well. The slow spin might be an illusion born from our incomplete picture of the chaos at the galaxy's heart. Resolving this mystery is more than an academic exercise. It cuts to the core of how these titans grow and how they shape their galaxies. A slow spin favoring chaotic accretion would paint M87 as a relentless, undiscriminating cannibal. A fast spin would suggest a more orderly, prolonged feast from a single direction. And if the jet thrives despite a slow spin, it means we must rewrite the textbooks on the most energetic engines in the universe. The quiet rotation of this giant may therefore hold the key to its violent past and the true source of the brilliant beam that has defined it for eons. Even the light from the most distant objects carries a chemical memory of its journey. When astronomers point their most powerful spectrographs at brilliant quasars lying far beyond Messier 87, they are not just looking at those beacons. They are using them as cosmic searchlights, probing the invisible material that lies in the vast foreground. As the quasar's light travels 55 million light-years or more to reach us, a tiny fraction of its journey takes it directly through the outermost reaches of Messier 87's immense halo. This halo is not empty. It is filled with a tenuous, nearly invisible fog of gas, a wispy atmosphere expelled from the galaxy itself over billions of years. When the quasar's pristine light passes through this fog, specific colors are subtly stolen, absorbed by atoms within the gas. The result is a series of dark notches etched into the quasar's spectrum called absorption lines. Each line is a barcode identifying a specific element at a specific distance. And here is the strangest part: many of these lines reveal the presence of metals, elements like carbon, oxygen, silicon, and iron, atoms far heavier than the primordial hydrogen and helium that filled the early universe. This is the signature of chemical pollution on an intergalactic scale. These metals did not form in the quasar, nor did they condense in the empty void. They were forged in the nuclear furnaces of stars that lived and died within Messier 87. Then they were violently expelled. The primary suspects for this galactic exhalation are the very forces we have explored, the active galactic nucleus and its powerful winds. Imagine a supernova explosion or a collective stellar wind near the galaxy's core. It blasts enriched gas outward, but that is just the first step. The colossal energy from the black hole's activity, Its periodic jet outbursts and radiation pressure then acts like a cosmic bellows. It sweeps up this metal-rich gas and pushes it further, accelerating it until it overcomes the galaxy's gravity entirely. This material streams out into the halo and beyond, becoming a permanent part of the intergalactic medium. By cataloging these absorption lines, astronomers can perform a kind of remote chemical cartography. They can map where these enriched clouds are, how fast they are moving, and crucially, what they are made of. The ratio of different metals tells a story. A pattern rich in alpha elements like oxygen and magnesium points to enrichment dominated by short-lived massive stars that died in core collapse supernova. A signature with more iron, however, suggests a major contribution from Type 1, a supernova, which take much longer to evolve. This allows scientists to date the pollution event to determine whether the gas was blown out in an early, frenzied burst of star formation, or in a more recent, violent episode linked to the black hole's activity. Each faint absorption line is therefore a message in a bottle, but the bottle is a cloud of gas 1,000 light-years wide, and the message was written by the combined lives and deaths of billions of stars, then mailed into the void by a monster. It reveals that a galaxy's influence does not end at the visible edge of its stars. Through these nearly invisible traces, Messier 87 is still declaring its presence, chemically tagging the cosmos with the elemental proof of its internal fires, and seeding the future with the raw materials for new generations of stars and planets in galaxies yet to be born. The very heart of this galactic giant is a place of profound emptiness. While we see a brilliant jet and a swirling maelstrom of hot gas, the immediate stellar neighborhood of the supermassive black hole is curiously quiet. Unlike the cores of many galaxies, including our own Milky Way, Messier 87 lacks a distinct, dense nuclear star cluster, a tight, blazing sphere of millions of stars that should, by all rights, orbit just outside the event horizon. Instead, the black hole M87 star sits in relative stellar isolation, a titanic monarch ruling a strangely depopulated inner court. This absence is a loud clue, a missing piece of architecture that tells a violent story about how this black hole grew to such an immense scale. In a typical large galaxy, the supermassive black hole and the nuclear star cluster are cosmic partners, often coexisting in a delicate balance at the dynamical center. The cluster is a relic of the galaxy's earliest, most intense period of star formation, a dense ball of ancient suns that sank to the core over billions of years. Its presence is expected, a standard feature of galactic construction. Messier 87's lack of such a cluster is therefore a glaring deviation from the norm. It forces us to ask what happened to it, or if it ever existed at all. One compelling narrative is a story of destruction by the very monster that now sits in the void. As the supermassive black hole grew, likely through a series of violent mergers with other black holes, the gravitational chaos in the core would have been unimaginable. During each merger, the resulting gravitational wave recoil could have sent the newly formed, more massive black hole oscillating through the dense star cluster like a cosmic wrecking ball. This process, called dynamical heating, would have violently scattered the cluster's stars, flinging them out into the wider galactic halo or even ejecting them entirely. Over billions of years, this relentless gravitational scattering could have completely dissolved the once dense cluster, leaving behind only the black hole and a diffuse, hot glow of stars in its immediate vicinity. The black hole, in essence, demolished its own palace to build a larger throne. Alternatively, the absence may point to a fundamentally different origin story for Messier 87 itself. Perhaps this galaxy never formed a distinct nuclear star cluster in the first place because it was assembled primarily through the mergers of other giant elliptical galaxies, which themselves may have lacked such clusters. Or the process that formed its supermassive black hole may have been so rapid and direct, a collapse of vast amounts of gas in the early universe, that it left no time or material for a dense stellar cusp to form around it. In this scenario, the black hole was born a solitary giant, and the galaxy built itself around this pre-existing gravitational anchor. This missing cluster is more than an architectural oddity. It has real consequences for the environment we observe today. A dense nuclear star cluster would act as a constant source of fuel for the black hole, as tidal forces and stellar collisions would regularly funnel stars and gas into its maw. Without it, the black hole's feeding must rely on more haphazard sources that diffuse hot gas, the occasional tidal disruption of a wandering star, or the rare merger event. This could explain why the black hole is currently in a relatively quiet, linear state despite its powerful jet. It simply doesn't have a steady, dense food supply at its doorstep. The emptiness at the center is thus a key to understanding the engine's current rhythm, a quiet that speaks of a past so violent it cleared the stage for the solitary drama now unfolding. The straight line of that brilliant jet is not as perfect as it first appears. Look closer and you might detect a subtle, sinuous curve, a gentle bending along its 5,000 light-year length. This is not a random wiggle, but a potential clue written in plasma, a phenomenon known as jet precession. Imagine the black hole and its accretion disk not as a static, rigid machine, but as a spinning top. If you knock a top slightly off its perfect vertical spin, it begins to wobble, its axis tracing a slow circle in the air. This wobble is called precession. Now scale that up to a cosmic monster. If the spin axis of the supermassive black hole M87 star is itself precessing, then the jet it launches would act like a lighthouse beam attached to that wobbling axis. Over thousands of years, the jet would slowly sweep out a cone in space, and from our distant viewpoint, we would see it not as a perfectly straight line, but as a gently curved arc. The very existence of such a curve would be a monumental discovery because in the realm of general relativity, a single, isolated black hole is a remarkably stable object. Its spin axis should remain fixed in space, locked in place by the conservation of angular momentum. For it to precess, something must be knocking it off balance, something with immense gravitational influence. The prime suspect is a hidden dance partner, a second, smaller black hole, perhaps hundreds of millions of times the mass of our Sun, could be locked in a binary orbit with M87 star. As these two titans whirl around each other, their mutual gravitational pull would act like an invisible hand, constantly tugging on the spin axis of the primary black hole, forcing it to wobble. The jet, forever tied to that axis, would therefore carry the imprint of this hidden orbital dance. Finding the precise signature of this precession is a task of exquisite measurement. Astronomers must compare high-resolution radio images taken decades apart, looking for minuscule shifts in the position of bright knots within the jet. They must also model the complex fluid dynamics of the jet itself, because its interaction with the surrounding intergalactic medium can also cause bends and kinks that mimic precession. Distinguishing a true gravitational wobble from a hydrodynamic ripple is one of the great challenges in deciphering this cosmic message. If confirmed, the precession would be indirect but powerful evidence for a binary black hole system at the galaxy's heart. It would solve multiple mysteries in one stroke. The flaring hotspot HST1 could be explained by the smaller black hole periodically injecting energy into the jet as it orbits. The offset active galactic nucleus might reflect the complex, shifting center of mass of the binary pair. Even the galaxy's strange, quiet core could be a result of the binary's gravity clearing out stars over billions of years. This subtle curvature, then, is more than a bend in a beam of light. It is a potential recording of a gravitational duet, a slow, stately wobble that encodes the presence, the mass, and the orbit of a hidden companion, turning the jet into a needle tracing the grooves of an invisible, spinning record. The chemical history of a galaxy is not written in its stars alone, but in the very air it breathes. enveloping Messier 87 is that immense atmosphere of multimillion-degree gas, visible only in X-rays. But this hot plasma is not a uniform soup. It carries a distinct chemical signature that changes with distance from the core, a pattern known as the metallicity gradient. By carefully measuring the X-ray spectra at different radii, astronomers have mapped how the concentration of heavy elements like iron, oxygen, and silicon varies from the inner furnace to the outer halo. What they find is a clear story of cosmic pollution and isolation. The gas closest to the galaxy's heart is heavily enriched, brimming with metals forged in the cores of countless stars and scattered by their explosive deaths. This is the legacy of the galaxy's most intense period of star formation, which occurred billions of years ago in the dense central regions. As massive stars lived fast and died young in colossal supernova explosions, they flooded the inner galaxy with newly minted elements, chemically seeding the surrounding gas for all time. The further out you go, however, the metallicity of the hot gas gradually declines. The outer reaches of the halo are more pristine, with a chemical composition closer to the primordial mix of hydrogen and helium that filled the universe after the Big Bang. This gradient is a fossilized record of the galaxy's construction. It tells us that the intense metal-forging activity was overwhelmingly centralized. The outer gas was never thoroughly mixed with the polluted material from the core, either because the supernova-driven winds weren't powerful enough to push heavy elements that far, or because the outer gas itself has a different origin. Some of this pristine material in the far halo may be the original, unprocessed gas that collapsed to form the galaxy's outermost parts, never participating in the inner drama of star birth and death. Another portion could be cold, metal-poor gas that has more recently fallen into the halo from the intergalactic medium, like a gentle rain of primordial matter diluting the enriched brew. This metallicity map is more than a static snapshot, it's a clock. By comparing the observed gradient to sophisticated computer simulations, astronomers can estimate the efficiency of those ancient supernova winds. How much energy did those explosions impart? How effectively did they stir and churn the galactic atmosphere? A steep gradient suggests the winds were relatively weak, leaving the heavy elements concentrated near their birthplace. A shallower gradient would point to powerful, galaxy-wide winds that thoroughly mixed the elements throughout the halo. The data from Messier 87 points to a history of potent but not overwhelming enrichment from the core. Every measurement of iron or oxygen in that hot X-ray glow is therefore a direct echo of a supernova that exploded billions of years ago. It transforms the galaxy's atmosphere into a layered chemical archive, where each shell of gas holds the fossilized breath of ancient stars, telling us not just how the galaxy lived, but how its earliest generations died to create the elemental foundation for everything that followed. The death of a star cluster is a slow, silent unraveling. While we search for the brilliant flares of single stars being torn apart, an even larger feast could be unfolding on a timescale too long for us to witness directly. This is the potential fate of a globular cluster, a tight ball of 1 million ancient suns that drifts onto a fatally close orbit around the supermassive black hole. Unlike the sudden, violent end of a single star, the disruption of an entire cluster would be a drawn-out, majestic dissolution. The immense tidal forces, the same difference in gravity that spaghettifies a star, would begin to work on the cluster as a whole. They would not rip it apart in an instant. Instead, they would gently but inexorably pull it like cosmic taffy, stretching it first into a long, stellar streamer that wraps around the black hole in a graceful, doomed ellipse. Over many orbits spanning perhaps hundreds of thousands of years, the stream would widen and diffuse, its stars scattering into the chaotic core, becoming indistinguishable from the background swarm. This process would not produce a brilliant, fleeting flare of light. The stars themselves are not being torn apart, only their gravitational bond to each other is being severed. They would be stripped away one by one like grains of sand from a ball of twine, leaving no sudden flash to catch our eye, yet the aftermath would leave subtle fingerprints. The sudden injection of 1 million new stars into the already crowded dynamics of the galactic core would create a faint but detectable stir. Computer simulations show it could slightly alter the average motions of stars in that region, a statistical blip in the velocity dispersion that a future, ultra-precise survey might one day detect. More tantalizing is the possibility of a secondary effect. A globular cluster is not just stars, it also contains a reservoir of interstellar gas and dust, along with countless stellar remnants, white dwarfs, neutron stars, and perhaps even intermediate mass black holes at its heart. As the cluster is shredded, this dense concentration of compact objects and gas could be funneled toward the central monster. This might not trigger a quasar-like eruption, but it could provide a sustained, low-level snack for M87 star, a slight brightening in the core's ultraviolet or X-ray output that lasts for centuries. It would be a gentle feeding, a cluster's worth of cosmic crumbs falling slowly into the abyss. Finding evidence for such an event would be a challenge in cosmic forensics. Astronomers would need to look for the faint, coherent stream of stars itself, a needle in a haystack of millions, or they might find a population of stars in the core with a distinct chemical signature, all matching each other but different from their neighbors, like a group of foreigners who arrived together and never fully assimilated. This would be the surviving members of the devoured cluster, their shared ancestry betrayed by the unique elemental patterns in their light. While we have not yet caught a cluster in the act of being destroyed, the very possibility reshapes our view of the galactic core. It is not a static arena, it is a dynamic ecosystem where not just gas and individual stars, but entire cities of stars are potential fuel. The slow, tidal dissolution of a globular cluster represents a different mode of black hole feeding, one of patience over violence, a billion-year process where a celestial community is quietly dismantled and its citizens scattered, adding one more layer of complexity to the already crowded and violent heart of the giant. This invisible sea of radiation is the galaxy's true atmosphere. Beyond the brilliant light and the hot X-ray gas, the space around Messier 87 is saturated with something far more elusive, a pervasive fog of ultra-high energy particles known as cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, that have been stripped of their electrons and accelerated to over 99% the speed of light. They are the ultimate shrapnel from the black hole's explosive power, and they fill the colossal cavities carved by the jet, creating an invisible pressure that shapes the galaxy's destiny. Imagine a balloon not filled with air, but with a furious, invisible wind of subatomic bullets. This is the environment surrounding this galactic giant. These cosmic rays are born in the most violent processes imaginable. Some are likely accelerated in the intense shock waves at the very launch point of the relativistic jet, near the black hole's event horizon. Others gain their unbelievable speed further out, within the turbulent internal shocks of the jet itself, or in the expanding walls of the X-ray cavities as they plow through the cluster gas. Once injected into the cavities, these particles become trapped. They spiral along the weak, tangled magnetic fields that also fill these voids, unable to escape easily, bouncing back and forth for millions of years. This transforms each cavity from a mere bubble of empty space into a pressurized container of pure energy, a cosmic battery storing the black hole's past outbursts. The influence of this cosmic ray atmosphere is profound and subtle. While the hot X-ray gas provides thermal pressure, the cosmic rays contribute a different kind of force, a relativistic pressure. This combined pressure is what helps the cavities buoyantly rise through the hotter, denser cluster gas, like a hot air balloon in the atmosphere. But the cosmic rays do more than just provide lift, they actively regulate the galaxy's future. One of their key roles is to suppress star formation on a galactic scale. For new stars to form, vast clouds of cold molecular gas must collapse under their own gravity. This process requires the gas to lose energy to cool down. The pervasive sea of cosmic rays interferes with this cooling in a critical way. As the hot gas tries to cool and condense, these high-energy particles can reheat it, imparting just enough energy to keep the gas puffed up and diffuse, preventing it from reaching the critical density needed for collapse. It is a gentle, pervasive form of feedback, a constant background hum of energy that maintains a stalemate against creation. This cosmic ray atmosphere also acts as a long-term reservoir of the black hole's power. The particles trapped by magnetic fields can linger for hundreds of millions of years, slowly leaking their energy into the surrounding medium. This provides a steady, low-level heating that prevents the hot galactic atmosphere from cooling catastrophically and raining down to form trillions of new stars in a single, unsustainable burst. It is the black hole's way of enforcing balance, using an invisible, energetic fog to thermostat its entire domain. Detecting this atmosphere directly is incredibly difficult as the particles themselves are invisible. But their presence is betrayed by the faint radio halo that envelops the galaxy, the synchrotron glow emitted as the cosmic rays spiral in magnetic fields. They are the unseen architects of that ghostly radio light. This means every time we see that faint, diffuse radio glow, we are not just seeing a relic, we are seeing the active, breathing atmosphere of a giant, an invisible sea of ancient fury that continues to write the rules for life and death across millions of light years. The brilliant knots in that jet may be flashing in a hidden rhythm. One of the most puzzling behaviors to decode is whether their eruptions are random, isolated events or part of a synchronized sequence. When the hotspot HST-1 flared so violently, astronomers watched closely to see if other knots closer to the core or further out brightened in response. The question is simple yet profound. Does the black hole's engine have a heartbeat, a regular pulse that sends waves of energy rippling down its colossal jet? If these eruptions are coordinated, it would point to a propagating disturbance. Imagine flicking a long, taut rope. A wave travels down its length, making different points along it jiggle in turn. In the jet, this wave could be a powerful shock front. A sudden injection of mass or a surge in magnetic energy at the black hole could launch a pressure wave through the magnetized plasma. As this shock moves outward at a significant fraction of light speed, it would compress particles and amplify magnetic fields, causing each knot it passes through to light up in sequence, a domino effect of cosmic fireworks. This would be a direct transmission of the black hole's momentary fury, a signal traveling down its own neural pathway. The alternative is a story of synchronized feeding. Perhaps the black hole does not consume gas smoothly, but in gulps. Dense clumps of matter from the accretion disk could fall in at semi-regular intervals, each one triggering a burst of energy that simultaneously lights up multiple pre-existing weak points along the jet's entire length. In this scenario, the knots don't brighten in a traveling sequence but all at once, or in a pattern that reflects the jet's internal structure, not a moving wave. It would be like turning up the voltage to a string of old Christmas lights, making all the dim bulbs glow brighter in unison. Distinguishing between these possibilities requires patient, long-term monitoring across the electromagnetic spectrum. Astronomers must create a timeline of eruptions for each distinct knot, mapping their brightening and fading against each other with exquisite precision. A clear time delay where a knot closer to the core flares first, followed by one further out days or weeks later, would be a smoking gun for a propagating shock. The speed of that propagation could then be calculated, telling us about the physical conditions within the jet itself. If the brightenings are simultaneous or chaotic, it points to a more global change in the engine state. So far, the evidence is tantalizing but not conclusive. HST-1's famous flares did not have an obvious, clean counterpart in other knots, suggesting it might be a local instability. Yet, smaller, coordinated brightenings have been seen in other jets, keeping the idea of a cosmic heartbeat alive. Finding this rhythm in Messier 87 would be like placing a stethoscope on the galaxy's core. It would allow us to listen not just to the monster's roars, but to its steady pulse, a fundamental cadence that governs how it channels unimaginable power into a beam that stretches across the cosmos. Even the mightiest structures in the cosmos are not fixed. The supergiant we have explored, with all its strange objects and violent history, is itself part of a slow, gravitational waltz that will one day rewrite the map of the Virgo Cluster. Messier 87's ultimate fate is written in its motion relative to a neighboring Titan, another giant elliptical galaxy known as Messier 86. Precise measurements of their velocities reveal they are not drifting apart, but are instead on a converging path, drawn together by their immense mutual gravity across the void. While the scale is almost beyond comprehension, the trajectory suggests that in perhaps 100 million years, these two galactic giants will experience a close encounter, a gravitational embrace that could last for eons before culminating in a full merger. This is not a prediction of chaos, but a forecast of cosmic destiny, the next inevitable chapter in a story of growth by collision. Imagine the scene not as a sudden crash, but as a stately billion-year tango. As they draw near, their vast halos of dark matter will be the first to interact, weaving together long before their stars ever touch. Tidal forces will begin to pull at their edges, stretching out immense plumes of stars and gas, creating new, temporary structures of light far grander than any we see today. The hot X-ray atmospheres of both galaxies will slam together, generating colossal shock waves that heat the gas to even more extreme temperatures, likely triggering a brief, brilliant flash of star formation in any remaining pockets of cold fuel. But the true spectacle will unfold at the hearts of these giants. Both Messier 87 and Messier 86 harbor supermassive black holes. Messier 87's, of course, is the 6.5 billion solar mass monster we know so well. Messier 86's central black hole, while less studied, is still a behemoth, likely weighing billions of suns itself. As the galaxies merge, these two gravitational demons will begin their own fatal dance. They will spiral toward the center of the new combined galaxy, shedding orbital energy by flinging stars away on hyperbolic trajectories. This process could take hundreds of millions of years, but the finale is inevitable. In the last moments before they coalesce into a single, even more supermassive black hole, their inspiral will warp space-time so violently that they will release a stupendous burst of gravitational waves, ripples in the fabric of reality that will radiate across the universe. The merger will also funnel vast new reservoirs of gas toward this new, combined monster, likely awakening it from its current, relatively quiet linear state. We could witness the birth of a quasar of unimaginable brilliance at the core of the new galaxy, a beacon that would outshine all the stars in the Virgo Cluster combined. The resulting galactic entity, a hybrid of two already colossal ellipticals, will be a true monster, perhaps the dominant gravitational force in the entire local universe for billions of years to come. It will have a globular cluster system numbering in the tens of thousands, a halo of stars stretched across millions of light years, and a central black hole with a mass exceeding 10 billion suns. This future collision reminds us that the cosmos is a work in progress. Every strange object we have catalogued within Messier 87, from its hypervelocity stars to its dark lane filaments, are merely temporary features in a life cycle measured in tens of billions of years. The galaxy we see today is just a single frame in a long film of construction and destruction. Its past was written by collisions, its present is defined by their aftermath, and its future is sealed by the same relentless gravity that built it. The dance with Messier 86 is already written into their trajectories, a silent promise of a cataclysm that will forge the next cosmic giant, resetting the clock for a new era of violent beauty in the heart of the Virgo Cluster. From its iconic shadowed heart to the faintest whispers of orphan stars, Messier 87 is a universe of strangeness contained within a single point of light. We have journeyed past the supermassive black hole's event horizon, traced the impossible speed of its jet, and wandered through ghostly streams of stars torn from cannibalized galaxies. We have witnessed unexplained flares in brilliant knots, hunted for missing stellar clusters, and mapped the chemical pollution this giant exhales into the void. Each of these 50 objects, from the hypervelocity stars to the dark lane filaments, represents a different question posed to the cosmos, a different extreme of physics laid bare. This is not merely a collection of curiosities, it is a complete cosmic laboratory. Messier 87 tests the limits of Einstein's gravity in the shadow of its black hole. It challenges our models of how galaxies grow through violent mergers, written in the lumpy asymmetry of its halo. It forces us to rewrite the rules of particle acceleration in its flickering tera-electron-volt light. Every observation is an experiment, and every strange feature is a result waiting for its theory. Yet for all we have uncovered, the greatest lesson may be one of perspective. If a single galaxy, one among hundreds of billions, can hold such an overwhelming diversity of mystery, then the universe is far stranger and more wonderful than we have dared to imagine. Our journey here is just a beginning. Each answer we find peels back a layer, only to reveal deeper, more profound questions waiting beneath, so stay curious. Look up at the night sky and remember that in the faint smudge of the Virgo Cluster, a giant is spinning its tales of creation and destruction. Which of its strange objects captured your imagination the most? Was it the violent jet, the lonely planetary nebulae between galaxies, or the haunting possibility of a hidden black hole binary? Share your thoughts and let's keep wondering together.